Picture this for a moment. You're strapped into the cockpit of the most advanced spaceship ever conceived. Outside your viewport, the familiar constellations smear into brilliant streaks of light, a kaleidoscope of color as you plunge forward into the inky black. Stars don't just twinkle, they race past you, transforming into hypnotic tunnels of pure energy. This is the fantasy of ultimate speed, the dream of crossing cosmic distances in the blink of an eye. But the reality of velocity in our universe is far stranger, more extreme, and more beautifully paradoxical than any science fiction could ever invent. It's a domain where some things move so fast they challenge the very fabric of reality, while others drift with such profound slowness that their journey is measured across the lifetime of stars. This is the breathtaking spectrum we're about to explore, a journey into the most astonishing speeds the cosmos has to offer. We often think of speed in simple terms: a car on a highway, a plane in the sky. But out there, in the grand theater of space, the rules are radically different. We're talking about the mind-bending velocities that govern everything, from the sluggish, glacial drift of entire galaxies through the void to subatomic particles hurtling at a staggering 99.9999% of the speed of light. It's a cosmic dance of energy and matter operating on a scale so immense, so alien to our daily experience, that it forces us to rethink everything we know about motion, time, and our place in the universe. These aren't just abstract numbers in a physics textbook. They are the fundamental forces that shape the cosmos from its first explosive breath and continue to dictate its ultimate fate. Understanding these extremes is like learning the secret language of the universe itself, a language written in velocity, and that is precisely the thrilling expedition we're embarking on today. We're going to count down 50 incredible facts about the universe's most extreme speeds, a curated tour of cosmic velocity that will take us from the achingly slow to the impossibly fast. We'll uncover how a seemingly stationary object on Earth is actually racing through space at millions of miles per hour, why there appears to be a universal speed limit, and what happens when something dares to challenge it. This is more than just a list. It's a story of motion, a narrative of how everything from the largest galaxy to the smallest particle is on an incredible journey. So get comfortable and prepare to have your perspective shifted, because we are about to dive headfirst into the exhilarating and often unbelievable world of cosmic speed. To truly begin our journey into the extremes, we must start with the most fundamental rule of the cosmos, the one that governs all motion, the speed of light. This isn't just another fast speed, it is the universe's ultimate, unwavering speed limit. Designated by scientists with the letter c, this constant has a precise value of 299,792,458 meters per second. To put that in perspective, at that velocity, you could circle the entire equator of our planet roughly 7.5 times in a single second. But the raw number is less important than the profound rule it represents. According to Einstein's theory of special relativity, nothing with any mass at all can ever actually reach this speed. As an object with mass moves faster and faster, its energy requirements don't just increase, they skyrocket exponentially. Imagine you're pushing a shopping cart and at first it's easy, but as you try to go faster, the cart inexplicably starts getting heavier and heavier. The closer you get to the speed of light, the more it feels like you're trying to push an entire planet and then a galaxy. To actually reach C, you would need an infinite amount of energy, which is simply impossible. This cosmic speed limit isn't a suggestion. It's woven into the very fabric of space and time. This single rule has staggering consequences for our understanding of reality. It means that cause must always precede effect. Information cannot travel faster than light, preserving the logical flow of the universe. This principle isn't just theoretical. The GPS in your phone or your car has to account for these relativistic effects because the satellites whizzing overhead are moving fast enough for time to pass for them at a microscopically different rate than it does for us on the ground. Without correcting for the rules set by sea, your navigation would be off by miles within just a few minutes. So, this ultimate speed limit is not a barrier to our ambitions, but rather a foundational pillar that defines the very nature of our existence, from the smallest particles to the largest cosmic structures. Yet, for all its absolute power, this cosmic speed limit comes with a truly mind-bending exception, one that leads us directly to our second astonishing fact. While nothing can travel through space faster than light, space itself has no such restrictions. The very fabric of the cosmos is stretching, and it can carry galaxies along for the ride at velocities that would make light seem slow. This is the monumental distinction that reshapes our entire understanding of the universe's motion. It isn't that galaxies are rocketing away from us through a static void like cars on a highway. Instead, imagine the universe as the surface of a partially inflated balloon. If you carefully place several small dots on that balloon, each dot representing a galaxy, and then you steadily blow more air into it, what happens? The dots don't magically scoot across the surface. They remain fixed in their relative positions on the rubber. Instead, it is the rubber itself, the very space between them, that expands. As a result, every single dot steadily moves away from every other dot. The farther apart any two dots are to begin with, the more stretching rubber lies between them, and the faster they appear to recede from one another. This elegant analogy perfectly illustrates cosmic expansion. Now, let's push this idea to its logical and frankly stunning conclusion. Because the universe is so vast and has been expanding for so long, there exists a distance so great that the amount of space between us and a far-off galaxy is growing at a rate that exceeds the speed of light. This creates a fundamental boundary known as the cosmic horizon. Any galaxy lying beyond that horizon is being carried away from us by the expansion of space itself faster than its light can ever hope to travel toward us through that same expanding space. Think of it as trying to run up a downward escalator that is moving faster than your top sprinting speed. No matter how hard you run, you make no upward progress. In the same way, the light photons emitted by those incredibly distant galaxies are fighting a losing battle against the stretching of the cosmos, forever unable to bridge the gap to reach our telescopes. This means there are entire collections of stars, perhaps civilizations and worlds, whose light has not yet reached us and, due to the accelerating expansion of the universe, never will. They are permanently erased from our observable universe, receding into a perpetual darkness from which no signal, no story, no whisper of their existence can ever escape. This isn't just a theoretical curiosity. It is the confirmed reality of our accelerating cosmos, a gentle but relentless force that is actively hiding most of the universe from our view, all because the stage upon which everything plays out is itself growing at an unstoppable, superluminal pace. While the expansion of space itself can carry galaxies away at unimaginable speeds, our own Milky Way galaxy harbors a mechanism for creating unparalleled velocity on a more local, but no less spectacular scale. We find our third astonishing fact not in the quiet void between galaxies, but in the chaotic, violent heart of our own cosmic home. Here, astronomers have discovered something extraordinary: hypervelocity stars, solitary suns hurtling outward so fast they are not merely orbiting the galaxy, they are actively escaping its gravitational grip forever. One of the most famous examples is a star known as S5HVS1, a stellar cannonball caught in the act of being flung from the Milky Way at a blistering speed of over 1,700 kilometers per second. To put that truly astronomical pace into perspective, at that velocity, you could travel from the Earth to the Moon in a mere 6 minutes. So, what cosmic catapult could possibly launch a star with such ferocious energy? The answer lies with the most dominant gravitational force in our galaxy, the supermassive black hole at its very center, Sagittarius A star. The most widely accepted theory for creating these stellar outcasts involves a celestial dance of three bodies, a binary star system, and the immense black hole. Imagine two stars locked in a mutual orbit, swinging a little too close to the gravitational monster at the galactic center. The incredible tidal forces from the black hole can violently disrupt this binary partnership. In a gravitational slingshot maneuver of almost unimaginable power, one of the stars is captured by the black hole, forced into a tight, bound orbit. Its partner, however, receives a tremendous gravitational kick, a transfer of energy so potent that it is sent careening outward, accelerating to a significant fraction of the speed of light as it breaks free from the entire galactic system. This isn't a gentle nudge, it's a cosmic ejection of the highest order. Once set on their new trajectories, these hypervelocity stars are destined for a profoundly lonely existence. They are no longer part of the vast spinning disk of the Milky Way. Instead, they become intergalactic travelers, their path set on an endless journey through the cold, dark, and nearly empty space between galaxies. They will continue to speed through this immense void for billions of years, solitary beacons with no planetary systems to warm, destined to eventually burn out alone in the profound darkness. Their discovery is more than just a record of speed. It is a brilliant piece of forensic evidence. By tracing the path of a hypervelocity star backward across the sky, astronomers can confirm the location and confirm the awesome power of the supermassive black hole at our galaxy's core, witnessing the aftermath of a gravitational event so powerful it can fling a sun into the abyss. If you thought a star flung across the galaxy was fast, prepare to encounter a celestial object that redefines the very concept of spin. We now arrive at the dizzying realm of pulsars, the cosmic lighthouses born from the explosive deaths of massive stars. These aren't just any stellar remnants, they are neutron stars, the incredibly dense cores left behind after a supernova, and some of them rotate at rates so furious they defy all intuition. The undisputed champion of this stellar spinning class is known as pulsar J1748-2446 AD. This particular neutron star completes a full 716 rotations every single second. To truly grasp that, consider this. In the brief time it takes you to blink your eyes, this object has spun around over 40 times. Now, let's translate that rotational speed into a linear velocity. While a pulsar is incredibly dense, it still has a physical size with a typical diameter of around 20 kilometers. Performing the math on an object spinning 716 times per second reveals that a point on its equator is moving at approximately 70,000 kilometers per second. That is an almost incomprehensible 24% of the speed of light. Imagine a sphere the size of a city, but with the mass of 1.5 of our suns, and its surface is moving at a quarter of the universal speed limit. The forces involved at that velocity are mind-numbing. If you took any ordinary object, a planet, a moon, even a star, and tried to spin it that fast, the centrifugal force would instantly overcome its own gravity, tearing it into a cloud of subatomic particles in a fraction of a nanosecond. So, what allows this pulsar to hold itself together? The answer lies in the almost supernatural strength of its own gravity. A neutron star's gravity is not just strong, it is 100 billion times more powerful than the gravity we experience on the surface of the Earth. This unimaginable force crushes matter into its most degenerate form, creating a substance so dense that a single sugar cube-sized piece of it would weigh as much as every single person on our planet combined. It is this phenomenal gravitational binding energy, this ultimate cosmic glue, that acts as an unbreakable containment vessel. The gravitational pull is so overwhelmingly powerful that it easily counters the unimaginable centrifugal forces trying to rip the star apart. Think of it like the ultimate kitchen blender, spinning at a rate that would instantly vaporize any blade or container we could possibly build. But this cosmic blender is made of a material and held together by a force so far beyond our engineering that it simply laughs at the centrifugal fury, maintaining its perfect spherical shape while whirling at a pace that pushes the very limits of physics itself. After witnessing the frantic spin of a pulsar and the explosive ejection of hypervelocity stars, it's almost calming to pull back and observe one of the cosmos's most majestic and deliberate movements, the stately orbit of our entire solar system around the heart of the Milky Way. We are all passengers on a truly grand cosmic voyage, one that unfolds on a timescale almost impossible for the human mind to fully comprehend. Our Sun, along with its entire family of planets, moons, and asteroids, is steadily tracing a vast circle through the galactic disk, moving at a velocity of around 230 kilometers every single second. That speed is far from sluggish in our terrestrial terms. It's a blistering 828,000 kilometers per hour. Yet, despite this incredible pace, the journey is so immense that it feels like the ultimate expression of slow motion. The reason is the sheer scale of the path we must travel. The Milky Way galaxy is roughly 100,000 light-years across, and our solar system is located about 27,000 light-years from the bustling center. To complete just one single loop around this galactic circuit, a journey astronomers poetically call a galactic year, our Sun requires approximately 230 million Earth years. To truly absorb the weight of that timescale, we need to connect it to our own planet's deep history. Consider this profound perspective. The last time our solar system was at this precise point in its galactic orbit, the Earth was a very different world. The supercontinent of Pangaea was only just beginning its slow, multi-million-year breakup. The first primitive mammals were tiny, shrew-like creatures scurrying in the shadows of a world dominated by massive reptiles. The mighty Tyrannosaurus Rex would not evolve for another 100 million years. The entire epic saga of the dinosaurs, from their rise to their cataclysmic fall, played out within less than a single galactic year. The entire timeline of human civilization, from the first cities to the modern era, occupies less than a single heartbeat in this grand celestial cycle. This gentle, lazy drift through the galaxy is the ultimate reminder that the universe operates on clocks calibrated for stars and galaxies, not for human lifetimes. It's a humbling and awe-inspiring thought that as you go about your day, our entire world, our entire history, is being carried along on this slow, curving river of stars, a single component in a dance of almost unimaginable grace and patience. But these immense, slow galactic orbits are just one part of the story, because galaxies themselves are not static islands. They are dynamic, breathing entities, and sometimes they breathe fire. This brings us to one of the most powerful and transformative forces in galactic evolution, the incredible velocity of galactic winds. Imagine not a gentle breeze, but a hurricane of cosmic proportions, a supersonic gale of superheated gas and energetic particles blasting outward from a galaxy at speeds reaching thousands of kilometers per second. These are not metaphorical winds, they are physical outflows of immense power, and they play a critical role in deciding a galaxy's fate. These galactic hurricanes are born from two primary sources of immense energy. The first is from regions of frantic star formation known as starburst galaxies. In these cosmic nurseries, stars are being born at a rate hundreds or even thousands of times faster than in our own quiet Milky Way. This frantic birth rate produces a huge population of massive, short-lived stars. These stars live fast and die young, ending their lives in spectacular supernova explosions. When you have thousands of these explosions occurring in a relatively small volume of space, the collective energy is staggering. It's like countless sticks of dynamite going off in concert, heating the surrounding gas to millions of degrees and creating a colossal pressure wave that violently pushes material out of the galaxy, forming what is known as a superwind. The second, and even more powerful, engine for these winds is found at the very heart of certain galaxies, where a supermassive black hole is actively feeding. As vast amounts of matter spiral inward toward the black hole's event horizon, they form a searingly hot, glowing disk of material. This accretion disk generates unimaginable friction and magnetic fields, which can funnel some of the infalling matter into tightly focused jets that shoot out from the poles of the black hole at nearly the speed of light. Even more broadly, the intense radiation pouring out from this process can push on the surrounding gas, much like the wind from a fan, but on a galactic scale. This creates a powerful outflow that can sweep through the entire galaxy. The impact of these high-velocity winds is nothing short of transformative. A galaxy is a delicate ecosystem for star birth, requiring vast clouds of cool, dense gas and dust to collapse and form new stars. A galactic wind, with its incredible speed and energy, acts as a regulatory mechanism. It blows this vital star-forming fuel right out of the galaxy and into the intergalactic medium. This process, dramatically illustrated in supercomputer simulations, shows these immense outflows as vast, cone-shaped structures of colorful gas erupting from the galactic disk or core. The visual effect is breathtaking, like a fountain of fire on a cosmic scale. By ejecting this raw material, the wind effectively puts a brake on the galaxy's ability to create new stars. It's a cosmic form of self-regulation. A starburst galaxy or an active black hole can, through its own intense activity, ultimately starve itself of the fuel it needs to sustain that very activity. This wind shapes the galaxy's future, influencing its size, structure, and the ultimate population of stars it will contain. In a very real sense, the ferocious speed of these galactic winds writes the final chapter in the story of a galaxy's evolution, demonstrating that sometimes the most creative forces in the universe are also the most destructive. After exploring the breakneck speeds of galactic winds and the stately orbit of our solar system, it's almost jarring to bring our focus down to our own planet, where some of the most transformative forces operate at a pace that feels, to our human senses, almost frozen in time. We now arrive at an entirely different kind of extreme speed, one that turns our very definition of the word on its head. This is the plodding, almost imperceptible pace of continental drift. The colossal tectonic plates that form the foundation of our planet's crust are in constant motion, but they move at a rate that seems laughably slow, an average of just 2 to 5 centimeters each year. To put that into a truly relatable context, that's roughly the same speed at which your fingernails grow. Think about that for a moment. The same gradual, unhurried progress you observe when you glance at your hands every few weeks is the very same pace at which entire continents, massive landmasses weighing quadrillions of tons, journey across the globe. It's a motion so slow that it is utterly undetectable over a single human lifetime, or even across the entire span of recorded human history. No one in ancient Rome or Egypt ever perceived their continent subtly inching away from another. The process unfolds on a timescale that belongs entirely to the Earth itself. Yet, to dismiss this motion as insignificant because of its slowness would be to completely misunderstand the awesome, patient power of geology. While the yearly movement is minuscule, the cumulative effect over millions of years is nothing short of world-changing. The force driving this motion is the immense heat from our planet's interior, which causes the semi-molten rock in the mantle to churn in massive convection currents. This slow but unstoppable circulation acts like a colossal conveyor belt, dragging the rigid tectonic plates along at their fingernails' pace. And over deep time, this gentle, persistent push is responsible for sculpting almost every major feature of our planet's surface that we recognize today. The majestic Himalaya mountains, home to the highest peaks on Earth, are the direct result of the Indian plate slowly but relentlessly colliding with the Eurasian plate over the past 50 million years. That slow motion crash, moving at just a few centimeters per year, has crumpled and thrust the land skyward, creating a breathtaking mountain range. Similarly, the vast Atlantic Ocean was born from this gradual movement. Around 200 million years ago, the supercontinent Pangaea began to be pulled apart by the same forces, and as the North American and Eurasian plates slowly diverged, the gap between them filled with magma that cooled to form new oceanic crust. What started as a tiny crack has now widened into an ocean thousands of kilometers wide, all from that same persistent, creeping motion. This reveals a profound truth about our universe. Extreme is not a synonym for fast. An extreme speed can be one that is profoundly, almost unimaginably slow, yet possesses a transformative power that no fleeting burst of velocity could ever hope to match. A meteorite might strike in a brilliant, violent instant, scarring the landscape, but it is the patient, inexorable crawl of the continents that truly builds and rebuilds the world over eons. It forges the mountains that influence our climate, opens the oceans that govern our weather patterns, and rearranges the very stage upon which the drama of life evolves and goes extinct. It is the ultimate reminder that some of the most powerful forces in the cosmos don't roar. They whisper, acting with a patience that transcends all human conception of time, steadily reshaping worlds one slow, deliberate centimeter at a time. From the patient, earth-shifting crawl of continental plates, we now catapult to the opposite end of the spectrum, confronting a form of speed so raw and energetic it arrives as a constant, invisible bombardment from the depths of space. This brings us to the phenomenon of cosmic rays, a torrent of high-energy particles perpetually raining down on our planet. The vast majority of these travelers are single protons or the nuclei of atoms, stripped of their electrons, and they are not merely fast. They are some of the fastest discrete objects ever measured, hurtling through the void at velocities that kiss the ultimate cosmic speed limit. These are not gentle streams of light, but bullets of matter, and their journey across the galaxy is one of the most violent and enduring mysteries in all of astrophysics. The origins of these ultra-fast particles are a topic of intense scientific detective work. For decades, astronomers have worked to identify the natural particle accelerators capable of achieving such phenomenal energies. One of the leading candidates are the colossal shock waves produced by supernova explosions. When a massive star dies, it blasts its outer layers into space at thousands of kilometers per second. This creates a rapidly expanding shell of debris, and the shock front that precedes it can act like a cosmic surfboard. Charged particles, like protons, can get caught in the immense magnetic fields of this shock wave, bouncing back and forth across it. With each crossing, they gain a tremendous boost of energy, much like a surfer being pushed faster and faster by an endless wave. Over thousands of years, this process can accelerate a single subatomic particle to energies millions of times greater than anything achievable in our most powerful human-built particle colliders, like the Large Hadron Collider. However, for the very highest energy cosmic rays, even supernova may not be powerful enough. Scientists now look to even more extreme and cataclysmic environments, such as the cores of active galactic nuclei, where material spiraling into a supermassive black hole generates jets of plasma moving at relativistic speeds, or the tumultuous regions around merging galaxy clusters. These cosmic powerhouses could potentially provide the final, unimaginable kick needed to send a particle on its way at nearly the speed of light. And then, there are the particles that defy all expectations, the ones that stand out even in this crowd of cosmic speedsters. This leads us to the single most extreme example ever recorded, an event so staggering it was named the "Oh my God" particle. Detected in 1991 by the Fly's Eye Cosmic Ray Detector in Utah, this was not a wave or a burst of energy, but a single, solitary proton. The numbers associated with it are almost comically absurd, pushing the boundaries of what we thought was physically possible for a lone piece of matter. This proton was measured to be moving at 99.99999999999999995% of the speed of light. To comprehend the energy it carried, physicists calculated that this one tiny subatomic particle possessed a kinetic energy roughly equivalent to a baseball hurtling at 90 kilometers per hour. Imagine all the energy of a professionally pitched fastball packed into a single proton a million times smaller than a grain of sand. The implications of such an entity are mind-shattering. According to the principles of special relativity, as an object approaches the speed of light, its mass effectively increases. For the oh my god particle, its relativistic mass would have been enormous. The sheer kinetic energy it carried was 40 million times greater than the protons accelerated in the Large Hadron Collider. For a fleeting instant as it slammed into the upper atmosphere, this one proton was, from its own frame of reference, carrying the energy of a brick wall. It serves as a humbling and electrifying reminder that the universe, in its most hidden and violent corners, operates natural accelerators whose power and ferocity we are only just beginning to glimpse. Now, let's turn our attention to one of the most visually stunning and violent environments in the known universe, the very edge of a black hole. Here, just before matter vanishes forever behind the event horizon, it doesn't just fall straight in. Instead, it gets caught in a cosmic maelstrom of unimaginable ferocity, forming a structure known as an accretion disk. Picture the most powerful whirlpool you could possibly imagine, but replace the water with superheated gas, dust, and even entire stars that have been torn apart by the black hole's tidal forces. This material doesn't just drift inward calmly, it spirals around the black hole at velocities that defy belief, often reaching a significant fraction of the speed of light. In some of the most extreme cases, the inner regions of these disks have been observed whipping around at speeds exceeding half the universal speed limit. That means a stream of incandescent plasma, thousands of kilometers across, is completing orbits in mere milliseconds, tracing a circular path so fast it would cross the entire United States and back again in less than a single second. The physics behind this incredible motion is a direct result of the black hole's overwhelming gravity. As material is drawn inward, it conserves its angular momentum, much like an ice skater pulling in their arms to spin faster. The closer the gas and dust get to the event horizon, the faster they are forced to orbit, accelerating to these mind-numbing relativistic speeds. But this breakneck orbital velocity is only part of the story. The real drama, and the source of the incredible energy we can detect from billions of light years away, comes from the friction and violence within the disk itself. Think of it not as a smooth, placid river, but as a chaotic, turbulent traffic jam on a cosmic scale. Different streams of gas in the disk, orbiting at slightly different speeds, rub against each other with unimaginable force. This internal friction generates immense heat, turning the accretion disk into a cauldron of plasma with temperatures that can soar to millions of degrees. To put that temperature in perspective, the surface of our Sun is a relatively cool 5,500 degrees Celsius. The inner regions of an active accretion disk are hundreds of times hotter. This phenomenal heat causes the disk to glow with a light brighter than entire galaxies, emitting energy across the entire electromagnetic spectrum. Most notably, it blasts out torrents of high-energy X-rays, which space telescopes like NASA's Chandra X-ray Observatory are specifically designed to detect. These X-rays are not a gentle glow, they are a scream of radiation, a direct testament to the incredible forces at work as matter is literally torn apart and superheated on its final journey. The energy output is so immense that it can't be explained by nuclear fusion like in a star. Instead, it's the much more efficient process of gravitational energy conversion. As material loses orbital energy through friction and spirals down into the gravitational well, a portion of its mass is directly transformed into pure radiation, following Einstein's famous equation. This process can convert matter into energy with an efficiency dozens of times greater than the nuclear fusion powering stars. It's the universe's most powerful and ruthless engine, a dynamo that takes matter and just before swallowing it forever, squeezes out a final, brilliant flash of light that we can see across the vast expanse of space. But for all the violence of black holes and cosmic rays, there is another kind of extreme speed at work in the cosmos, one that unfolds with a strange, terrifying grace. This is the slow, inevitable death of a star like our own Sun, a process that redefines what we mean by speed on a stellar scale. For billions of years, our Sun has been a model of stability, fusing hydrogen into helium in its core at a steady, life-giving pace. But this balance is temporary. In about 5 billion years, the hydrogen fuel in its core will finally be exhausted. With the central fusion engine sputtering out, the outward pressure that has supported the star against its own immense gravity will falter. The core, now composed of inert helium, will begin to contract under its own weight. This is the trigger for one of the most dramatic transformations a star can undergo. As the core collapses, it releases a tremendous amount of gravitational energy, heating the surrounding layers of the star to unprecedented temperatures. This intense heat ignites hydrogen fusion in a shell surrounding the now inert core. The energy from this shell fusion pushes outward with far more force than the core's fusion ever did, causing the star's outer layers to expand at a staggering rate. In human terms, the expansion seems slow. It will take hundreds of millions of years to complete, but in the context of a star's multi-billion-year life, this is a breathtakingly rapid and violent change. The Sun will swell to hundreds of times its current diameter, its surface cooling and turning a deep, ominous red as it becomes a red giant. During this expansion, the star's outer layers are moving outward at speeds of tens of kilometers per second. While this is slow compared to a hypervelocity star, it is an unstoppable, swelling tide of plasma. As it grows, the Sun will first engulf and vaporize the planet Mercury, then Venus, and finally, it will likely reach the orbit of Earth. Our world, if it hasn't already been stripped of its atmosphere and oceans by the star's increasing luminosity, will be swallowed whole, spiraling into a fiery demise within the Sun's tenuous but searingly hot outer atmosphere. This grand, slow-motion explosion is only half the story, however. The fate of the star's core presents a stunning contrast in velocity. While the outer layers billow outward, the core continues its relentless collapse. It becomes a cosmic battleground, squeezed by gravity and heated to over 100 million degrees until it reaches a tipping point. In a flash known as the helium flash, the core ignites helium fusion, forging it into carbon and oxygen. This new fusion source provides a temporary reprieve, but it is short-lived. Once the helium-2 is exhausted, the core faces its final collapse. There is no fuel left to burn. What happens next is a spectacular release of energy that involves matter moving in profoundly different ways. The dying star ejects its entire outer envelope into space, creating a beautiful planetary nebula, a glowing shell of gas expanding outward at speeds of 20 to 30 kilometers per second. This is the star's final farewell, a slow and elegant bloom of color that will eventually fade. Meanwhile, the exposed core, now a white dwarf, is a celestial object of incredible extremes. This Earth-sized remnant contains roughly half the original mass of the star, making it phenomenally dense. Its collapse is ultimately halted not by fusion, but by a quantum mechanical force known as electron degeneracy pressure, the simple refusal of electrons to be squeezed any closer together. The formation of this white dwarf is a process of incredible compression. The matter that once made up the star's core is crushed together at speeds that, while not relativistic, involve immense gravitational acceleration, packing a sun's worth of mass into a sphere no larger than our planet. The surface gravity of a white dwarf is so intense that if you could stand on it, you would weigh hundreds of thousands of times what you do on Earth. This remnant will no longer generate new energy through fusion. It simply glows with the leftover heat from its dramatic birth, a brilliant, dense ember that will slowly cool over trillions of years, eventually fading to a cold black diamond in the dark of space. The death of a sun is thus a symphony of speeds, the slow, majestic expansion of a red giant, the faster, explosive expulsion of a nebula, and the ultimate, super-dense compression into a silent white dwarf, each stage governed by a different and extreme velocity. Just when you thought a spinning pulsar represented the peak of a neutron star's ferocity, we encounter an even more volatile and terrifying class of these stellar remnants, the magneta. If a typical neutron star is a cosmic cannonball, a magneta is that same cannonball wrapped in the most powerful magnetic field known to exist in the entire universe. To even begin to comprehend the strength of this field, consider the magnet that holds your shopping list to your refrigerator. That has a magnetic field strength of about 100 Gauss. The Earth's own protective magnetic field measures roughly half a Gauss. A strong medical MRI machine might reach 10,000 Gauss. Now, prepare for a number that truly defies imagination. A magneta's magnetic field registers at approximately 1 million billion Gauss. This is a level of magnetic energy so concentrated, so ludicrously powerful, that it fundamentally alters the vacuum of space around the star. If a magneta were located halfway between the Earth and the Moon, its magnetic field would effortlessly strip the information from every credit card on our planet. Get any closer and the field itself would become lethal, warping the electron clouds in every atom of your body, effectively dissolving you from the inside out. This is the stage set with almost unimaginable force for one of the most violent and rapid events in all of cosmology, the starquake. A neutron star's crust is not a soft, pliable surface. It is an ultra-dense, crystalline lattice of atomic nuclei, a crust of iron 1,000,000 times stronger than steel, all held together by that immense gravitational pressure. But even this supermaterial is no match for the internal strain caused by a magneta's evolving magnetic field. These fields are so strong they actually exert a tangible force on the star's structure, twisting and stressing the crust over time. It's akin to slowly bending a giant cosmic metal bar. Eventually, the stress becomes too much and the crust can no longer hold its shape. It suddenly catastrophically cracks and shifts, rebounding into a new, more stable configuration. This is the starquake, and its release of energy is nothing short of apocalyptic. In a mere thousandth of a second during the initial rupture, a single starquake can unleash more energy than our sun will radiate across the entire electromagnetic spectrum over 100,000 years. Let that timescale sink in. All the light, heat, and radiation that our steady, life-giving star produces for 1,000 centuries is outpaced in a single, brilliant millisecond by a crack in a star's crust 20 kilometers across. This instantaneous, colossal release of energy does two extraordinary things. First, it acts as the ultimate particle accelerator. The catastrophic shifting of the crust and the realignment of the magnetic field lines launch a blast of protons and electrons, accelerating them to velocities so close to the speed of light that they become relativistic, their mass effectively increasing as they tear through the magneta's magnetosphere. Second, this storm of high-speed particles channeled by the intense magnetic fields generates an intense flash of radiation, primarily in the form of gamma rays and hard X-rays. For a brief moment, the magneta becomes the brightest object in the gamma ray sky, outshining every other source in our galaxy combined. These flashes, known as soft gamma repeaters, are not the long-duration gamma ray bursts from stellar collisions. They are shorter, incredibly intense pulses that can be detected by satellites orbiting Earth from clear across the Milky Way. One of the most famous recorded events, the gamma-ray flash from magneta SGR 1806-20 in 2004, was so powerful that it actually ionized the upper layers of Earth's atmosphere from 50,000 light-years away, strongly affecting low-frequency radio waves across the planet. It was a palpable tremor in our own planet's electronic veil, a direct and humbling signal from a catastrophic event halfway across the galaxy. The magnetar's starquake thus represents a perfect storm of cosmic extremes, the incredible density of a neutron star, the universe's most powerful magnetic fields, and a rupture that unfolds in a millisecond, yet whose aftermath we can witness from staggering intergalactic distances. It is a stark reminder that violence and beauty in the cosmos are often two sides of the same coin, a coin spinning in the depths of space. After witnessing the stellar violence of magnetars and the slow death of suns, it's grounding to return our gaze to our own planet, where another kind of extreme motion is perpetually at work, one that carves the very ground beneath our feet with a patience that rivals geology itself. We find this in the colossal rivers of ice known as glaciers. To the casual observer, a glacier appears as a frozen, static monument, a seemingly permanent fixture of the landscape. But this is a profound illusion. Glaciers are, in fact, in constant motion, flowing downhill with a slow, inexorable power that is almost imperceptible from one day to the next, yet utterly transformative over centuries. Their speeds exist on a fascinating spectrum, from the barely their creep of just a few centimeters a day in cold, polar regions to the surging, rapid flow of tens of meters per day in certain fast-moving outlets. This movement isn't a simple, solid slide like a block of ice on a ramp. It's a complex dance of physics driven by two primary mechanisms working in concert. The first is a process known as internal deformation. Think of a glacier not as a brittle sheet of ice, but as an incredibly viscous, slow-moving fluid. The immense weight of thousands of feet of overlying ice exerts tremendous pressure on the deepest layers. This pressure, combined with the constant force of gravity, causes the individual ice crystals to microscopically shift, rotate, and slide past one another. The entire ice mass slowly oozes and stretches, deforming under its own weight like a piece of warm tar, gradually flowing downhill in a process that affects the glacier from its surface all the way to its base. The second, and often more significant, mechanism is basal sliding. For this to occur, the glacier must be at or above its pressure melting point at the base. The colossal weight of the ice creates such immense pressure that it actually lowers the melting point of the ice at the very bottom, creating a thin film of meltwater that lubricates the interface between the glacier and the underlying bedrock. This watery layer allows the entire mountain of ice to literally slide over the ground, greatly accelerating its journey. The terrain itself plays a crucial role. If the bedrock is smooth, the sliding is more efficient, but if it's rough and uneven, the glacier must deform and creep around the obstacles, a process that can create deep crevices and seracs on the surface above. To truly appreciate the power of this creeping motion, we must borrow the eyes of time-lapse photography. Imagine compressing centuries into a few seconds. What seems from our human perspective to be a frozen, immobile expanse is suddenly revealed as a dynamic, flowing river of solid ice. You would see the glacier's central channel moving faster than its edges, which are slowed by friction with the valley walls. You would witness its tributaries, smaller glaciers, merging into the main flow like the branches of a great, slow-motion tree. And most importantly, you would see its profound and relentless impact on the landscape. This is where the glacier's slow speed reveals its true earth-sculpting power. As it advances, the glacier acts as the most powerful excavator imaginable. The base of the ice, studded with embedded rocks and debris, grinds against the underlying bedrock like a colossal sheet of sandpaper, a process called abrasion that polishes and smooths vast areas of stone. Larger, protruding rocks act like chisels, gouging deep, parallel scratches called striations into the bedrock, providing permanent evidence of the glacier's passage. Even more dramatic is the process of plucking, where meltwater seeps into cracks in the bedrock at the glacier's base, freezes, and then, as the glacier moves, literally rips giant boulders loose, incorporating them into the ice and further quarrying the landscape. The cumulative effect of this slow, grinding advance over thousands of years is some of the most breathtaking scenery on Earth. The entire majestic topography of places like Yosemite Valley, the Swiss Alps, and the fjords of Norway is a direct testament to glacial power. Those vast U-shaped valleys with their steep, straight walls were not carved by rivers which create V-shaped canyons. They were widened and deepened by glaciers that flowed through them like slow-moving rivers of concrete, scouring away everything in their path. The towering, sheer face of Half Dome in Yosemite is a monument to the glacier that carved away its other half. The deep, serene waters of a fjord are simply a glacial valley that was later flooded by the sea, a permanent scar left by ice that has long since retreated. This demonstrates a universal principle that applies from geology to our own lives. A force, no matter how seemingly weak or slow, when applied persistently and consistently over a long enough period, can achieve results that a brief, violent burst of energy never could. A meteor strike creates a sudden crater, but a glacier, moving no faster than your hair grows, can patiently and methodically erase entire mountains and reshape continents, reminding us that true power often resides not in speed, but in unwavering, relentless persistence. If you thought the furious spin of a pulsar or the explosive power of a magnetar represented the upper limits of cosmic violence, then prepare for a phenomenon that truly dwarfs them both. We now turn our attention to a spectacle of speed and scale that is almost incomprehensible: the relativistic jets powered by active galaxies. Imagine an engine of almost unimaginable power, a supermassive black hole at the core of a distant galaxy, feeding ravenously on the gas, dust, and even entire stars that spiral into its clutches. But this cosmic monster is not a tidy eater. As matter spirals inward at a significant fraction of light speed, forming a searingly hot accretion disk, not all of that material is doomed to cross the event horizon. Through processes we are still striving to fully understand, a portion of this infalling matter is instead channeled and focused by the black hole's mind-boggling spin and unimaginably powerful magnetic fields. The result is a pair of tightly collimated beams or jets that erupt from the black hole's rotational poles, shooting out into intergalactic space in opposite directions. These are not gentle streams of light. They are fire hoses of pure energy composed of a superheated soup of electrons, protons, and other subatomic particles, a state of matter known as plasma. And the velocity at which this plasma is ejected is the stuff of legend. We are not talking about mere percentages of light speed. We are talking about a flow that has been clocked through intricate astronomical observations at over 99% of the universe's ultimate speed limit. A jet like this is a celestial express train, barreling through the cosmos at a pace where the normal rules of time and space begin to warp and bend in profound ways. The sheer physical scale of these structures is as breathtaking as their speed. A single relativistic jet can extend from its source for hundreds of thousands, even millions of light years. To put that in perspective, our entire Milky Way galaxy is roughly 100,000 light-years across. These jets, therefore, can be 10 times longer than our entire galactic home, stretching far beyond the boundaries of their host galaxy and punching deep into the emptiness of intergalactic space. They are the largest coherent structures in the entire universe, and their formation is a masterclass in cosmic engineering. The key to their incredible length and narrow focus lies in the process of collimation. You might expect such a powerful eruption to spray out in a wide, unfocused cone, like water from a broken fire hydrant. Instead, these jets remain pencil-thin over their mind-boggling length. This is the work of the intense magnetic fields generated by the churning, dynamo-like action of the accretion disk itself. These magnetic fields act like a perfectly shaped nozzle, wrapping around the jet and pinching it into a tight, coherent beam that prevents it from dissipating and spreading out. It is this magnetic confinement that allows the jet to maintain its ferocious energy and punch through the interstellar and intergalactic medium for such vast distances. When one of these relativistic jets is pointed almost directly at Earth, we witness the most consistently luminous objects in the entire cosmos, quasars. The word quasar is actually a shortening of quasi-stellar radio source, because when they were first discovered, they appeared as star-like points of light, yet their spectra revealed they were anything but ordinary stars. A single quasar, powered by the engine of a supermassive black hole and its jet, can outshine an entire galaxy of hundreds of billions of stars. The light from one quasar can be 1,000 times more brilliant than our entire Milky Way. This staggering luminosity does not come from nuclear fusion like in a star. It is generated by the raw, terrifying power of gravity itself. As material in the accretion disk rubs together at relativistic speeds, it is heated to temperatures of millions of degrees, causing it to glow intensely across the electromagnetic spectrum, from radio waves to gamma rays. But the jet adds another layer of brilliance. As the high-speed plasma in the jet interacts with magnetic fields or slams into slower-moving material in its path, it produces intense, focused emission, particularly in the radio part of the spectrum. This makes quasars and other active galaxies with jet's beacons that can be seen clear across the observable universe, serving as cosmic lighthouses that help us map the large-scale structure of the cosmos. The existence and behavior of these relativistic jets provide astronomers with a natural laboratory for studying physics under conditions of energy, density, and velocity that we could never hope to recreate on Earth, pushing our understanding of the fundamental laws that govern everything we see. After witnessing the universe's natural particle accelerators and the relativistic jets that stretch across millions of light years, it's profoundly humbling to bring our focus back to the incredible, yet comparatively modest, speeds achieved by our own human ingenuity. Our fastest spacecraft are magnificent testaments to engineering and ambition, but they operate in a different league entirely from the cosmic phenomena we've been exploring. The current reigning champion of human-made speed is NASA Parker Solar Probe, a mission of almost unbelievable daring designed to touch the Sun. On its closest dives through the Sun's searing outer atmosphere, the corona, this resilient spacecraft will use our star's own immense gravity as a slingshot, accelerating to a breathtaking velocity of approximately 700,000 kilometers per hour. That translates to about 195 kilometers every single second. To put that staggering human achievement into a relatable context, at that speed, you could travel from New York to Tokyo in less than a minute, or circle the Earth's equator more than 4 times in just 1 hour. It is, without a doubt, the fastest object humanity has ever created. Yet, when we place this remarkable number alongside the cosmic speed limit of 299,792,458 meters per second, the perspective shifts dramatically. The Parker Solar Probe's blistering pace amounts to a mere 0.064% of the speed of light. This stark comparison isn't meant to diminish our accomplishments, but rather to illuminate the sheer scale of the challenge that true interstellar travel represents. The vastness of space is the ultimate obstacle. Consider our nearest stellar neighbor, the Proxima Centauri system, located about 4.24 light-years away. Even if we could magically instantiate the Parker Solar Probe on a direct course toward it, traveling at its maximum speed, the journey would take over 66,000 years. That's a time span longer than all of recorded human history. This simple calculation reveals the fundamental problem with our current propulsion technologies. They are simply too slow by cosmic standards. We are, in essence, paddling a canoe across an ocean the size of a planet. This immense gulf between our current capabilities and the velocities required for practical starflight forces us to confront the brutal physics of interstellar travel. The primary challenge isn't just achieving a high speed, It's achieving that speed in a way that is sustainable and, crucially, controllable for a vessel carrying a crew or delicate instruments. The energy required to accelerate even a modestly sized spacecraft to a significant fraction of light speed is astronomical. To reach just 10% of light speed, a small probe would require an amount of energy comparable to all the electricity the entire United States consumes in an entire year. And that's just for acceleration. You would need a similar, immense amount of energy to slow down upon arrival, unless the plan is a fleeting, high-speed flyby that would last only seconds. This is why science fiction concepts like warp drives or hyperspace are so appealing. They propose clever, hypothetical loopholes to the problem of moving through space by instead manipulating space itself. While such ideas are fascinating theoretical playgrounds for physicists, they remain firmly in the realm of speculation, requiring materials or forms of energy, like exotic matter with negative mass, that we have no evidence actually exist or can be manufactured. For now, our most plausible path to the stars relies on more patient, long-term technologies. Projects like Breakthrough Starshot envision using powerful ground-based lasers to push tiny, gram-weight probes equipped with light sails to 20% of the speed of light. While this would get a fleet of microprobes to Alpha Centauri in about 20 years, it is a far cry from sending humans or even substantial robotic explorers. The journey of the Parker Solar Probe is a magnificent first step, a demonstration that we can navigate and survive in the most violent environments our solar system has to offer. But it also serves as a powerful and necessary reality check, grounding our stellar ambitions in the hard, unforgiving numbers of physics and reminding us that the highway to the stars remains, for now, a road we only just begun to map. From the patient grind of glaciers to the incredible velocities of relativistic jets, our tour of cosmic speed has revealed a universe of breathtaking variety. But sometimes the most valuable motion isn't the fastest one in an absolute sense, but the most reliable and rhythmic. This brings us to a special class of stars that act as the universe's own metronomes, their steady pulse providing the fundamental rhythm by which we can map the cosmos. These are the Cepheid variable stars, celestial lighthouses whose predictable flickering has unlocked one of astronomy's greatest challenges, measuring the vast distances between galaxies. At first glance, a Cepheid variable might seem like any other bright, massive star, but watch it over days or weeks and you will witness a remarkable transformation. The star doesn't just twinkle due to Earth's atmosphere, it genuinely changes its intrinsic brightness, swelling and shrinking in a slow, rhythmic dance. Picture a cosmic heart beating with a period that can range from a single day to well over a month. This isn't a random sputter or a catastrophic explosion, it's a stable, self-regulated pulsation. The physics behind this stellar heartbeat is a delicate balancing act between two opposing forces. In the star's outer layers, a region of partially ionized helium acts like a sophisticated heat engine. When the star is at its smallest and densest, this helium traps radiation from the core, heating up and causing the gas to expand. As the star swells, it cools and the helium recombines, becoming more transparent. This allows the trapped radiation to escape, reducing the outward pressure and allowing gravity to pull the outer layers back inward. The cycle then begins anew, creating a continuous, self-sustaining oscillation. During this pulsation, the star's outer layers are in constant, dramatic motion. As the star expands, its surface races outward at speeds that can reach tens of kilometers per second. When it contracts, that same surface comes rushing back inward at a comparable pace. While these speeds are modest compared to a hypervelocity star, they are far from trivial. This rhythmic expansion and contraction involves the movement of a significant portion of the star's own mass. This entire process, the changing size and the accompanying change in surface temperature, is what causes the star's brilliance to vary so noticeably. A Cepheid doesn't just get bigger and smaller, It gets brighter as it expands and hotter, and dimmer as it contracts and cools. This regular, predictable pattern of brightening and dimming is the star's unique signature, and here is where their true cosmic value lies. In the early 20th century, the brilliant astronomer Henrietta Swan Leavitt made a groundbreaking discovery while studying hundreds of these variable stars in the small Magellanic Cloud. She noticed a clear and direct relationship. The longer the pulsation period of a Cepheid, the greater its intrinsic luminosity. A Cepheid that takes 40 days to complete a full pulsation cycle is inherently much brighter than one that pulses with a 5-day period. This period luminosity relationship was a revelation. It meant that astronomers could simply measure how long it took a Cepheid to pulse, and from that alone, they could determine its true power output, its absolute magnitude. Once you know how bright a star truly is, and you measure how dim it appears from Earth, calculating its distance becomes a relatively straightforward exercise. It's like knowing the exact wattage of a light bulb. If you see it shining faintly in the distance, you can calculate just how far away that bulb must be. This single discovery transformed Cepheid variables into the first reliable standard candles for measuring distances beyond our own galaxy. They became the crucial rungs on the cosmic distance ladder. It was by using Cepheids that Edwin Hubble was able to measure the distance to the Andromeda Galaxy, proving conclusively that it was a separate island universe far outside the Milky Way, forever shattering the notion that our galaxy was the entire cosmos. Later, by correlating the distances to galaxies measured by Cepheids with the redshifts of those same galaxies, Hubble discovered the expansion of the universe itself. The steady, rhythmic pulsation of these stars, with their surfaces moving at tens of kilometers per second, provided the key evidence for the greatest cosmological discovery of the 20th century. They are the fundamental calibrators that allow us to measure the scale of everything, from nearby star clusters to the vast voids between galactic superclusters, their gentle oscillation echoing as a dependable heartbeat across the expanding universe. While we've been charting the breakneck speeds of cosmic objects and the patient grind of geological forces, there's one celestial motion happening right above our heads that profoundly connects the two, a gradual drift of profound consequence. The moon, our constant companion in the night sky, is in fact slowly leaving us. Every single year, due to the intricate gravitational dance between the Earth and the moon, our lunar partner moves about 3.8 centimeters farther away. That's roughly the same rate at which your fingernails grow, a gentle but relentless retreat that has been underway for billions of years and will continue for billions more. The engine behind this cosmic migration is the force of tides. The moon's gravity doesn't just pull on the solid Earth, it exerts a powerful tug on our planet's fluid envelopes, most visibly the oceans. This pull creates the familiar bulges of water we know as high tides. However, because the Earth rotates on its axis so much faster than the moon orbits around us, our planet's spin actually drags these tidal bulges slightly ahead of the imaginary line directly connecting the Earth and moon. This forward-leaning bulge of ocean water, in turn, exerts its own gravitational pull on the moon. This subtle but constant tug does two remarkable things. First, it acts like a gentle, continuous gravitational slingshot, pulling the moon forward in its orbit and feeding it energy. In orbital mechanics, adding energy to an object causes its orbit to expand. So, this process ever so slightly boosts the moon into a higher, and therefore slower, orbit, making it recede from us year after year. This is the reason for that annual 3.8 centimeter gain in distance. But this celestial exchange doesn't come without a cost for Earth. The energy that is being transferred to the moon has to come from somewhere, and it is siphoned directly from the Earth's own rotational momentum. Think of it as a form of cosmic friction. The gravitational interaction between the Earth and its tidal bulges creates a braking force, acting to slow down our planet's spin. This means our days are getting ever so slightly longer. The effect is minuscule on a human timescale. A day lengthens by only about 1.7 milliseconds per century. You would never notice it in your lifetime, but when compounded over the deep history of our planet, the numbers become staggering. Back when the Moon first formed from the debris of a giant impact over 4 billion years ago, an Earth day was likely only 5 or 6 hours long. The planet was a spinning top with a furious cycle of day and night. Since then, the relentless transfer of Earth's rotational energy to the Moon's orbit has steadily applied the brakes, stretching our day out to the 24 hours we know today. If we project this slow-motion ballet far into the future, we can see its ultimate conclusion. As the Moon continues to recede, its apparent size in our sky will slowly shrink. Total solar eclipses, that breathtaking cosmic coincidence where the Moon perfectly covers the Sun, will eventually become a thing of the past. The Moon will be too far away to completely obscure the solar disk, leaving only annular or ring of fire eclipses. Furthermore, the breaking of Earth's rotation will continue. In about 50 billion years, if the Sun was still shining, the Earth and Moon would reach a final state of stability known as tidal locking. In this distant future, the Earth's rotation would slow so much that a single day would last as long as a single lunar month. From the surface of Earth, the Moon would hang motionless in the sky, visible only from one hemisphere of our planet. The other half of the world would never see it again. The gravitational transfer of energy would cease, the Moon's recession would halt, and the system would find a quiet equilibrium. Our world would be a vastly different place, with days and nights each lasting nearly 47 of our current days, fundamentally altering climate, weather, and the very rhythm of life itself. This gentle, centimeter-by-centimeter retreat is a powerful reminder that even the most seemingly permanent fixtures in our sky are part of an endless, dynamic cosmic dance, one that is quietly reshaping our world on a timescale that humbles all of human history. If you thought the slow, rhythmic pulsations of a Cepheid variable or the gentle recession of the Moon represented the more patient side of cosmic motion, then prepare for a spectacle of pure, unadulterated violence. We now arrive at one of the most transformative and energetic events in the entire universe, the supernova. This is not a star's gentle sigh, it is its final, defiant roar, a self-immolation of staggering power that, for a few glorious weeks, can outshine an entire galaxy of stars. And at the very heart of this cosmic detonation is a shockwave of such ferocious speed and force that it literally reshapes the future of its galactic neighborhood. Picture a massive star many times heavier than our Sun, reaching the end of its life. For millions of years, it has been a delicate balancing act, with the outward pressure from nuclear fusion in its core perfectly countering the immense inward pull of its own gravity. But that balance is about to shatter. When the star finally exhausts its nuclear fuel, the fusion engine in its core sputters and dies. Instantly, the outward pressure vanishes. There is nothing left to hold back the star's own colossal weight, and the core collapses inward at a quarter of the speed of light. In less than a single second, a core that was once the size of the Earth is crushed into an ultra-dense sphere no larger than a city, a neutron star, or, for the most massive stars, a black hole. The energy released by this catastrophic collapse is almost beyond comprehension. It rebounds from the impossibly hard surface of the newborn neutron star, creating a titanic pressure wave that blasts outward through the star's still infalling outer layers. This is the birth of the supernova shockwave. This is no ordinary sound wave or ripple. It is a wall of energy and matter that erupts from the dying star's core, accelerating the star's own outer layers to velocities that can reach a staggering 30,000 kilometers per second. That is 10% of the speed of light. To grasp that scale, imagine taking the entire bulk of a giant star, a sphere of incandescent gas millions of miles across, and hurling its outer shells into the void so fast that they could cross the entire United States in a thousandth of a second. The initial flash of light is blinding, but the real work of cosmic engineering is done by this expanding sphere of stellar debris, a tsunami in space that propagates for thousands of years. As this supersonic shockwave plows into the cold, quiet gas and dust of the interstellar medium, it doesn't just push it aside. It slams into it with unimaginable force, compressing the thin material into incredibly dense, wispy sheets and filaments. We can see the gorgeous, ghostly remnants of these collisions in telescopes, like the delicate Veil Nebula, which is the scattered wreckage of a star that exploded thousands of years ago. This compression is the universe's primary mechanism for triggering a new cycle of star birth. The shockwave acts like a cosmic snowplow, gathering up diffuse clouds of hydrogen and helium and squeezing them until their internal pressure and temperature become so high that the force of gravity takes over, causing these new, denser pockets to collapse and ignite into a new generation of stars. Our own solar system is likely the product of such an event, seeded by the heavy elements and triggered into formation by the shockwave from a long-dead stellar ancestor. But the shockwave's role is even more profound than just stellar midwifery. It is also the universe's primary distributor of the very ingredients for life. For its entire life, the star was a nuclear forge, fusing hydrogen into helium, and then, in its final stages, creating heavier elements like carbon, oxygen, and silicon in its layered interior. The supernova explosion itself, with its immense temperatures and pressures, generates a final, frantic burst of nuclear fusion, creating the heaviest elements of all, like gold, silver, and uranium. All of these newly forged elements, the carbon in our cells, the oxygen we breathe, the iron in our blood, the calcium in our bones, are trapped inside the star's ejected layers. The supernova shockwave is the delivery vehicle. It takes this enriched stellar material and blasts it across light years of space, scattering these essential heavy elements far and wide, where they will eventually become part of new gas clouds, new planets, and ultimately new life. Every time you look at your own hand, you are looking at stardust that was forged in the heart of a massive star and then flung across the galaxy by the incredible, star-shattering speed of a supernova shockwave. This breathtaking cycle of death and rebirth, driven by one of the fastest and most violent events known, is a powerful testament to a fundamental truth of the cosmos, that from the most extreme destruction often comes the most vital and beautiful creation. After witnessing the explosive, rapid-fire deaths of massive stars in supernova, it's almost a relief to discover a stellar population that operates on an entirely different clock. One so profoundly slow that it redefines our very concept of a star's lifetime. This brings us to the quiet, unassuming, yet overwhelmingly common red dwarfs. If the universe's massive stars are the brilliant, short-lived fireworks, then red dwarfs are the steady, glowing embers that will outlast everything else. These are the smallest and coolest true stars, often no larger than the planet Jupiter, and their claim to cosmic fame is not their brilliance but their incredible longevity. While a star like our Sun will live for roughly 10 billion years before meeting its dramatic end, a typical red dwarf has a projected lifespan measured not in billions but in trillions of years. To grasp the sheer magnitude of that timescale, consider that our entire universe is only about 13.8 billion years old. This means that not a single red dwarf that has ever ignited has had even a fraction of the time required to burn out. The very first red dwarfs to form are still in their cosmic infancy, with trillions of years of stable fusion still ahead of them. The secret to their incredible endurance lies in their internal engine and their highly efficient use of fuel. Stars like our Sun are profligate spenders. They burn through their hydrogen fuel at a furious rate in a large, chaotic core, creating immense outward pressure and shining brightly. A red dwarf, by contrast, is the ultimate model of energy efficiency. Its lower mass means the gravitational pressure at its core is far less intense, resulting in a much lower temperature and pressure. This gentler environment prevents the star from fusing hydrogen in the same way. Instead of a large, churning core, a red dwarf undergoes a process called convective mixing. The entire star, from its core to its surface, is in constant, slow motion, like a pot of thick soup simmering on a low flame. This complete circulation ensures that fresh hydrogen is continuously cycled down into the core to be fused, while the helium ash produced by fusion is carried away. This process is incredibly slow and methodical, allowing the star to consume its entire vast reservoir of hydrogen fuel over an almost incomprehensible span of time. The star isn't just siphoning fuel from a small central tank. It's meticulously using every single drop of hydrogen it possesses. This remarkable stability makes red dwarfs the ultimate long-term residents of the cosmos. While larger stars will flare up and die, and galaxies will eventually run out of the gas needed to form new ones, the red dwarfs will simply keep on shining. Their light will persist long after every other stellar class has faded away. This leads to a fascinating and almost philosophical implication for the future of life in the universe. Many red dwarfs are known to host rocky, Earth-sized planets within their habitable zones, the region where temperatures could allow for liquid water. However, life in such a system would face unique challenges. Red dwarfs are often prone to powerful stellar flares, especially in their youth, which could bombard nearby planets with intense radiation and potentially strip away their atmospheres. Furthermore, because these stars are so faint, their habitable zone is located very close in. A planet orbiting within this zone would likely become tidally locked, with one side in perpetual, scorching daylight and the other in eternal, freezing night. The thin band of twilight between these two extremes, known as the Terminator line, has been suggested as a potential oasis where life could theoretically cling on. The journey for any life evolving on such a world would be a slow and patient one, unfolding over hundreds of billions of years under the constant, dim, crimson glow of a star that barely changes. These stellar embers will be the last sources of warmth and light in a cooling universe, the final beacons in the vast, darkening cosmos long after all other stellar fires have been extinguished. Now let's turn our gaze to a different kind of cosmic traveler, one whose appearance has captivated humanity for millennia, but whose true nature holds a surprising secret of motion. We're talking about comets, those beautiful, ethereal visitors that grace our night skies. At first glance, a comet's magnificent tail seems to trail behind it, like the long hair of a runner streaming backward as they sprint forward. It's an intuitive assumption, but it's also completely wrong. In reality, a comet's tail is not a trail of where it has been, but a flag pointing almost directly away from where it is going. This celestial signpost is created not by the comet's motion through space, but by the relentless, invisible push of our sun. As a comet, often described as a dirty snowball made of ice, dust, and frozen gases, swings in on its elongated orbit and gets closer to the sun, the increasing solar heat causes its surface to sublimate. This means the ices turn directly from a solid into a gas without ever becoming a liquid, releasing vast clouds of gas and dust particles into the space around the nucleus. This cloud forms a vast, glowing envelope called the coma, and it is here that the sun takes over. Our star constantly emits not just light, but a stream of charged particles known as the solar wind, blowing outward in all directions at speeds of around 400 kilometers per second. It also exerts a constant, gentle push with the force of its own radiation. These two forces, the solar wind and radiation pressure, act like a cosmic leaf blower, sweeping the material of the coma away from the sun. This is why a comet's tail always points away from the sun, regardless of whether the comet is flying inward on its approach or outward on its departure. If you could see a comet's path from above the solar system, its tail would swing around like the beam of a lighthouse, always pointing radially away from the sun, a behavior that is beautifully counterintuitive. But a comet doesn't just have one tail. It typically has two distinct tails, each composed of different materials and moving at dramatically different speeds, which gives them their unique and ghostly appearance. The first is the dust tail. This is composed of tiny, solid particles of dust and rocky material that were once embedded in the comet's ice. Because these particles are heavier and more influenced by radiation pressure than the solar wind, they are pushed away more slowly and tend to curve slightly, following the broader arc of the comet's own orbit. This gives the dust tail a soft, broad, and often yellowish-white appearance as it reflects the sunlight. It's the slower, more languid component of the comet's display. The second tail, however, is where true velocity takes over. This is the ion tail, also known as the plasma tail. It is made of gas from the coma that has been ionized by the sun's ultraviolet radiation, meaning its atoms have lost electrons, becoming electrically charged. Because they are charged, these particles become intimately coupled to the magnetic fields carried by the solar wind. They don't just drift away, they are grabbed and accelerated along the magnetic field lines, funneled directly away from the sun at astonishing speeds. While the dust tail might move at a comparatively sedate pace, the ion tail can be accelerated to hundreds of kilometers per second. This incredible velocity, combined with the specific way its gases emit light, is what gives the ion tail its distinctive, ethereal blue color. You can often see this in photographs of famous comets like Hale-Bopp or Neowise, a bright, sharp, straight blue tail seeming to spear directly away from the sun, with a softer, curving white tail following a slightly different path. This blue ion tail is a real-time visualization of the solar wind itself, a high-speed river of particles that we normally cannot see, made brilliantly visible only when it interacts with the vapors of a passing comet. It's a stunning reminder that even in the apparent serenity of the night sky, forces of immense speed and power are constantly at work, shaping the cosmos in ways we can only perceive through these fleeting, beautiful interactions. From the silent, persistent ticking of a comet's ion tail to the patient trillions of years glow of a red dwarf, we've seen how the cosmos measures time in many different ways. But there is another kind of clock hidden deep within the very fabric of matter itself, one that ticks with a slowness so profound it has literally shaped the world beneath our feet. This is the incredible, almost imperceptible process of radioactive decay, particularly as seen in elements like uranium-238. The concept of speed here takes on a different meaning entirely. It's not about velocity through space, but about the statistical rate at which an unstable atomic nucleus spontaneously transforms, a process that unfolds on a timescale that makes the age of the universe seem almost brief. The key to understanding this is the idea of a half-life, which is the time it takes for half of any given sample of a radioactive isotope to decay. For uranium-238, that half-life is approximately 4.5 billion years, remarkably close to the entire age of our planet Earth. Think about that for a moment. If you had a small, pure piece of uranium-238 when the Earth first formed, only half of it would have transformed into other elements by now. The other half would still be waiting for its turn, ticking away at a rate that is utterly undetectable to any of our senses. So, what is actually happening during this unimaginably slow process? In the case of uranium-238, the primary mechanism is something called alpha decay. Deep within the nucleus, a cluster of 2 protons and 2 neutrons, effectively a helium nucleus, becomes unstable relative to the immense forces holding the atom together. Through the strange probabilities of quantum mechanics, this alpha particle can sometimes tunnel through the energy barrier that normally confines it. When this happens, the particle is ejected from the nucleus at a tremendous speed, often around 15,000 kilometers per second, which is about 5% of the speed of light. So, the ejection itself is a remarkably fast event, but the speed we're focusing on is the frequency of these events across a vast population of atoms. For any single atom of uranium-238, the chance of it decaying in any given second is almost infinitesimally small. It's like having a mountain with a single, specific grain of sand buried deep inside, and you are only allowed to check one random grain every century. The odds of you finding that specific grain are astronomically low, yet given enough time, it is a statistical certainty. This is the nature of radioactive decay. It is governed by probability, not by a deterministic countdown, and for certain elements, that probability dictates a pace of change that is glacial beyond human comprehension. This gentle, persistent release of energy from deep within the Earth has had consequences of world-shaping importance. Every time an atom of uranium or other radioactive elements like thorium or potassium-40 decays, it releases a tiny amount of energy in the form of heat. Now, multiply that single, nearly insignificant event by the quadrillions upon quadrillions of atoms present throughout the Earth's mantle and crust. The cumulative effect of all these infinitesimally slow decays is the primary source of our planet's internal heat. This geothermal energy is the engine that drives the convection currents in the mantle, which in turn power the movement of tectonic plates. The slow crawl of the continents, the eruption of volcanoes, the building of mountains, all of these grand geological processes that we discussed earlier are ultimately fueled by the gentle, radioactive warmth generated by atoms decaying over billions of years. Without this internal heat source, Earth's mantle would have cooled and solidified long ago. Our planet would be geologically dead, and the surface would be a far more static and likely lifeless place. The immense slowness of the decay is precisely what allows it to be a long-term energy source, providing a steady, reliable warmth that has persisted for eons and will continue for billions more. This reliable pace also provides us with one of the most powerful tools in all of science, radiometric dating. Because the half-life of an isotope like uranium-238 is a fixed and known value, it acts as a perfect natural clock. When a mineral crystal forms, such as within a cooling magma, it often incorporates trace amounts of uranium into its structure. At the moment of crystallization, the clock starts ticking. The uranium atoms are the parent isotope, and they begin their slow, stately transformation into lead, which is the stable daughter isotope. By carefully measuring the ratio of the remaining uranium-238 to the lead-206 that has accumulated within a rock sample, geologists can calculate precisely how long ago that rock solidified. This single method has allowed us to peer deep into Earth's history, providing definitive ages for the oldest rocks on our planet and the meteorites that formed alongside it, giving us the 4.54 billion-year age for the Earth itself. It allows us to construct a precise geological timescale, placing the rise and fall of dinosaurs, the formation of supercontinents, and the emergence of the first life into a firm chronological framework. The ability to read this natural clock, one that ticks with such profound and reliable slowness, has fundamentally reshaped our understanding of our own planet's story, revealing a past of almost unimaginable depth, all measured by the patient, inevitable decay of an unstable nucleus. But what if a pulsar didn't have to slow down? What if this cosmic spinner could be rewound and spun back up to an even more dizzying pace? This brings us to the remarkable phenomenon of the millisecond pulsar. While the pulsar we discussed earlier is a spectacular example of natural spin, these millisecond pulsars are the product of a bizarre cosmic partnership, a stellar dance that transforms an old, slowing pulsar into the most precise timekeeping device in the universe. The story begins with a typical neutron star, born from a supernova and spinning rapidly, but gradually slowing over hundreds of thousands of years as its powerful magnetic field acts as a brake, radiating energy away into space. This solitary pulsar would eventually become a slow, blinking relic, but its fate can be dramatically altered if it has a companion star. In a binary system, if the companion star evolves and begins to swell, its outer layers can spill over onto the neutron star. This isn't a gentle trickle, it's a torrent of matter transferring an immense amount of angular momentum. As this gas spirals onto the pulsar's surface, it acts like a cosmic whip, delivering a continuous push that spins the pulsar faster and faster. This process, known as recycling, can accelerate the pulsar's rotation from a leisurely few seconds per spin to a frantic few milliseconds, all while clearing out the surrounding space and effectively shutting off its previously strong magnetic field. The result is a celestial metronome of unrivaled stability, a pulsar that completes hundreds of full rotations every single second without missing a beat. The precision of these millisecond pulsars is almost beyond belief, so perfect that their rhythmic pulses can be predicted with an accuracy that rivals, and in some cases surpasses, the most advanced atomic clocks here on Earth. Atomic clocks might lose or gain a second over millions of years. A millisecond pulsar maintains its rhythm over similarly vast timescales through the immutable physics of its own incredible rotation. It's a stability born from its sheer mass and density. With the weight of a sun compressed into a city-sized sphere, it possesses a phenomenal moment of inertia. Nothing in the universe is bumpy or uneven enough to disrupt its spin in any detectable way. This makes them not just curiosities but powerful tools for fundamental physics. Astronomers use them as the ultimate cosmic laboratories, exploiting their predictable flashes to test the very fabric of space-time as described by Einstein's theory of general relativity. By meticulously tracking the arrival times of pulses from a pulsar in a binary system with another neutron star, scientists can measure tiny deviations in the orbit. They can observe how the intense gravity of the two stars causes the system to lose energy in the form of ripples in spacetime itself, gravitational waves. The first indirect evidence for gravitational waves, which earned a Nobel Prize, came from precisely this kind of observation of a binary pulsar system, confirming a key prediction of Einstein's theory decades before we could detect the waves directly. This application has since evolved into an even more ambitious endeavor, using a whole array of these cosmic clocks to try and detect the faint, background hum of gravitational waves washing through our galaxy. This is the goal of pulsar timing arrays, which monitor dozens of millisecond pulsars across the Milky Way. The concept is brilliantly simple. Imagine a sea of nearly perfect clocks scattered throughout space. Now, imagine a very long wavelength gravitational wave, perhaps from the merger of supermassive black holes in the hearts of distant galaxies passing through our region of the cosmos. As it passes, it will minutely stretch and squeeze the space between the Earth and one pulsar, then between the Earth and another. This subtle distortion will cause the pulses from some pulsars to arrive ever so slightly early and from others ever so slightly late in a correlated pattern across the sky. It's like trying to detect a gentle, universe-sized tide by observing how it affects the rhythm of lighthouses placed on islands thousands of light years apart. The effect is infinitesimally small, a distortion of time measured in tens of nanoseconds over years of observation. But the incredible stability of millisecond pulsars makes even this seemingly impossible measurement feasible. They have transformed from fascinating stellar remnants into the most sensitive components of a galaxy-sized observatory, allowing us to listen for the collective echo of millions of cosmic collisions, a low-frequency chorus that has been ringing through the universe since its earliest epochs. Now we arrive at a concept so fundamental it touches the very nature of reality itself, the speed of gravity. For centuries, we imagined gravity as an instantaneous force, a mysterious connection where one object, like the sun, could somehow reach out and pull on another, like the Earth, with no delay whatsoever. But Einstein's theory of general relativity completely rewrote this script. It proposed that gravity isn't a force in the traditional sense, but rather a curvature of spacetime caused by mass and energy. A massive object like the sun creates a depression in this four-dimensional fabric, and the Earth moves along the curves of this depression, much like a marble rolling around in a bowl. And just as a ripple on a pond takes time to travel outward from a dropped pebble, any change in this gravitational curvature, say, if the Sun were to suddenly vanish, would also propagate outward as a wave, a gravitational wave. Critically, Einstein's equations showed that these ripples in spacetime must travel at a specific, finite speed, the speed of light. This means the information about a change in gravity cannot travel any faster than the universe's ultimate speed limit. We wouldn't feel the Sun's disappearance gravitationally for the same 8 minutes it would take for its final ray of light to reach us. The news of its absence would arrive at the speed of causality itself. For decades, this prediction remained a beautiful but unconfirmed piece of theoretical physics. Detecting these incredibly faint ripples in spacetime seemed almost impossible. That all changed spectacularly on August 17, 2017, with an event that marked a true golden moment for modern astronomy. Observatories around the world, including the twin LIGO detectors in the United States and the Virgo detector in Italy, registered a distinctive chirp of gravitational waves. The signal told a clear story. Two incredibly dense objects, later identified as neutron stars, were locked in a final, deadly dance, spiraling inward and ultimately merging in a cataclysm about 130 million light-years away. This detection alone was historic, but what happened next, just 1.7 seconds later, elevated it to the realm of the legendary. The Fermi Gamma Ray Space Telescope, along with other observatories, detected a powerful flash of gamma-ray radiation coming from the exact same region of the sky. These gamma rays were the electromagnetic signature of the violent merger itself. The fact that the gravitational waves and the gamma rays arrived at Earth within a window of just seconds after traveling for 130 million years was the conclusive proof. The implications of this near-simultaneous arrival are profound. Both the gravitational waves and the gamma-ray photons were unleashed by the same cosmic event and began their journey across the universe at the same instant. They traveled through the void for over 100 million years, and they arrived at our detectors almost together. This meant that the carrier of the gravitational force, the ripples in spacetime, was moving at the same velocity as the particle of light, the photon. The speed of gravity had been measured, and it was within a tiny margin of error, exactly the speed of light. This observation didn't just confirm a century-old prediction. It fundamentally united our understanding of how information and forces are transmitted through the cosmos. It demonstrated that the fabric of spacetime itself is a medium that communicates changes at a finite, universal speed, ensuring that cause and effect remain firmly in place, even across the most immense distances. This event was more than just a discovery. It was the opening of a new sense for humanity, allowing us to not just see the universe, but to feel its vibrations, to listen to the very space-time we inhabit as it rings like a bell from the most violent events imaginable. While our solar system's grand 230 million-year orbit around the galactic center provides a sense of cosmic stability, there's a much more intimate and dynamic journey happening simultaneously. Our Sun, and all of us along with it, is sailing through the local interstellar medium, the sparse collection of gas and dust that fills the space between stars. This isn't a leisurely drift. We are moving relative to our immediate neighborhood at a brisk 25 kilometers per second. To visualize this, imagine our entire planetary system as a magnificent ship with the Sun at its helm, cutting through a gentle but persistent interstellar breeze. This motion has a profound effect on the invisible protective bubble that surrounds us, a structure known as the heliosphere. The heliosphere is our solar system's first line of defense, a vast region of space dominated by the solar wind, that constant stream of charged particles blowing outward from the Sun in all directions. Think of the solar wind as the engine exhaust of our star, and the heliosphere is the enormous bubble this exhaust inflates within the surrounding interstellar material. It acts like a cosmic force field, pushing back against the incoming flow of galactic cosmic rays, which are high-energy particles from distant supernova and other violent events. Without this bubble, these rays would constantly bombard our planets, potentially making the space environment far more hazardous for life and even influencing our climate. The shape of this protective bubble is not a perfect sphere. It's sculpted by the pressure of the interstellar medium pressing in from the outside and the push of the solar wind from the inside. But because our solar system is in motion, the bubble becomes distorted, taking on a shape much like a bullet or a moving raindrop. In the direction we're traveling, the bow of our cosmic ship, the heliosphere, is compressed. Here, the outward pressure of the solar wind collides head-on with the incoming interstellar wind, creating a boundary known as the bow shock, a region where particles are heated and slowed. In the opposite direction, the heliosphere stretches out into a long, comet-like tail, often called the heliotail. In this wake, the solar wind has more room to expand before it finally surrenders to the pressure of the galaxy. This asymmetrical structure was dramatically confirmed by data from NASA's Voyager probes, which have now crossed the final boundary of the heliosphere, known as the heliopause, and are truly traveling in interstellar space. Their readings showed that the boundary is not a static wall, but a dynamic, rippling surface that breathes and shifts with the sun's activity and the changing density of the local interstellar cloud. This ongoing interaction creates a turbulent region where the sun's particles mix with those from the galaxy, a frontier zone that is critical for filtering the harshest of the cosmic rays before they can reach the inner solar system. So, while we are shielded by our star's magnetic personality, that shield is constantly being molded and tested by our swift passage through the galaxy's subtle currents, a reminder that even in the relative quiet of our cosmic neighborhood, we are never truly at rest. Drifting through the vast galactic halos far above the brightly lit disk of the Milky Way are silent, ghostly rivers of primordial gas, colossal structures known as high-velocity clouds. These are not delicate wisps, they are immense reservoirs of neutral hydrogen, some stretching for hundreds of thousands of light years, making them larger than many galaxies we observe. What makes them truly extraordinary, however, is their motion. They are hurtling through our galactic neighborhood at speeds exceeding 100 kilometers per second, velocities that are completely anomalous when compared to the orderly rotation of the Milky Way's spiral arms. They are cosmic interlopers on a grand scale, and their origin story is a key piece in the puzzle of how galaxies like our own breathe, grow, and sustain themselves over billions of years. The predominant theory for the existence of these speeding clouds points to a birth during the universe's most formative era. They are considered by many astronomers to be the leftover building blocks of galaxy formation, pristine fossils from a time when the cosmos was a much more chaotic and crowded place. In the early universe, vast filaments of dark matter acted as a cosmic scaffolding, guiding normal matter, mostly hydrogen and helium gas, into the nodes where the first galaxies would eventually coalesce. The thinking is that not all of this primordial gas successfully made it into the galaxies. Some of these vast streams may have been left behind, lingering in the extended dark matter halos that surround galaxies like our own. For eons, they have been orbiting in the distant outskirts, a dormant fuel supply waiting in the wings. Their high velocities, then, are not from a recent explosive event, but are simply a reflection of the immense gravitational potential they are orbiting within. They are falling along great arcs toward the Milky Way, their speed a natural consequence of that long, slow gravitational descent from the intergalactic heights. A second, more violent origin story involves the messy process of galactic cannibalism. Our Milky Way is not a solitary island universe. It is the dominant member of a small group of galaxies, surrounded by dozens of smaller dwarf satellite galaxies. The immense gravitational pull of our galaxy creates devastating tidal forces, and when one of these satellites ventures too close, it can be literally torn apart. Its stars may be strewn across space to form faint stellar streams, but its gas content, being more loosely bound, can be easily stripped away. This stripped gas, now a massive cloud of neutral hydrogen, is flung outward, retaining much of the orbital velocity of its parent galaxy, but now set on a new, unpredictable path as a high-velocity cloud. The famous Magellanic Stream, a gigantic ribbon of gas trailing behind our large and small Magellanic Cloud galaxies, is a spectacular and active example of this process in action. It is a high-velocity cloud in the making, a direct pipeline of gas being forcibly donated to the Milky Way from its orbiting companions. Regardless of their origin, the ultimate fate of these clouds holds profound implications for the life cycle of our galaxy. The Milky Way's capacity to form new stars is entirely dependent on its supply of cool, dense gas. However, in the process of star formation, that gas gets locked away for billions of years inside stars, and a significant portion is even blown back out into space by supernova, now heated to such extreme temperatures that it is difficult for it to collapse and form new stars again. This is where the high-velocity clouds become essential. They represent a fresh infusion of fuel, a supply of pristine, unused hydrogen that has not been cycled through previous generations of stars. As these clouds eventually plunge into the galactic disk, their immense mass and velocity create powerful shock waves. These shocks compress the incoming gas as well as the gas already in the disk, triggering the gravitational collapse that leads to the birth of new stellar nurseries. In this way, these silent, dark clouds are the galactic delivery trucks, bringing in the raw materials that will one day coalesce into new suns and planetary systems, ensuring that the Milky Way's star-forming factories do not run out of fuel. They are a vital component of a galaxy's long-term evolution, a beautiful demonstration of how even the most seemingly empty spaces are connected to the vibrant, shining disk in a continuous cycle of birth and renewal. But for all the cosmic journeys and intergalactic velocities we've explored, one of the most significant speeds in your daily life is one you can't feel at all, happening right under your feet. Let's talk about the surprisingly fast spin of our own planet. While it feels like you're standing perfectly still, if you're on the equator, you are actually whizzing through space at about 1,670 kilometers per hour due to Earth's rotation alone. To put that into a more dramatic context, that's significantly faster than the speed of sound, which travels at around 1,235 kilometers per hour. You are quite literally a supersonic traveler on a planetary scale carousel, completing a full circle every 24 hours without ever sensing the motion. The reason we remain blissfully unaware of this incredible velocity comes down to a simple principle of physics: constant velocity. Because the Earth rotates at a steady, unchanging rate and we are moving along with it, the ground, the atmosphere, and everything attached to it, there's no accelerating force to signal our brains. It's the same reason you don't feel like you're moving when you're cruising at a constant speed on a smooth airplane flight. You only feel the changes in motion like during takeoff or turbulence. Our entire environment moves in sync, creating a stable, local reference frame that completely masks the planet's frantic spin. This unseen rotation, however, leaves its fingerprints everywhere, most notably through a fascinating phenomenon known as the Coriolis effect. Because the Earth is a sphere, different parts of it rotate at different linear speeds. A point on the equator has to cover the planet's full circumference in 24 hours, hence its high speed, while a point near the pole traces a much smaller circle in the same time, moving much more slowly. This difference in rotational speed creates an apparent force that deflects the path of any object moving freely over long distances. It's not a true force pushing things, but rather a result of an object's inertia as the planet rotates underneath it. Imagine you're on a merry-go-round and you try to throw a ball directly toward the center. From your perspective on the spinning platform, the ball appears to curve off to the side, even though from an outside view, it's traveling in a straight line. You and the merry-go-round are simply rotating away from its path. The Coriolis effect works in exactly the same way on a global scale, and its consequences are written into the very patterns of our world's weather and oceans. In the atmosphere, this deflection is the master choreographer of large-scale wind systems and storms. As air moves from high-pressure areas to low-pressure areas, the Coriolis effect bends its path. In the northern hemisphere, the deflection is to the right of the direction of travel, while in the southern hemisphere, it's to the left. This is why hurricanes and typhoons, those colossal engines of wind and rain, spin in a counter-clockwise direction north of the equator and a clockwise direction to the south. The system simply couldn't organize itself into such a tight, rotating vortex without the Coriolis effect guiding the inward rushing winds into a spiral. Similarly, the great persistent wind belts of our planet, the trade winds, the westerlies and the polar easterlies, are all shaped by this invisible hand, a direct product of our planet's rapid rotation. The influence extends powerfully into the oceans as well, driving the great conveyor belts of marine currents that regulate the Earth's climate. Major ocean currents like the Gulf Stream in the Atlantic, which carries warm tropical waters northward to moderate the climate of Western Europe, are steered by the Coriolis effect. As surface water is pushed by the wind, the deflection causes it to pile up slightly, creating gentle slopes in the ocean surface. The water then flows downhill under gravity, but is continuously deflected, resulting in the large, circular currents known as gyres that dominate each ocean basin. This movement is crucial for distributing heat around the globe, making some regions far more habitable than they would otherwise be. So the next time you watch a weather forecast showing a massive storm system spinning its way across a continent, or you learn about a current that carries warmth to a distant shore, remember that you are seeing the invisible signature of our planet's own high-speed rotation, a silent, swift motion that quietly orchestrates the dynamic systems of our world. While we've explored the frantic spin of pulsars and the explosive power of supernova, let's now step into a realm where time moves with an almost geological patience, a place where the very worlds we call home are slowly sculpted from the faintest whispers of dust and gas. This brings us to the profoundly slow and majestic process of planet formation. Far from the instantaneous flash of a cosmic explosion, the birth of a planet is a story of persistence, a gradual accumulation that unfolds over millions of years within the swirling cocoon of a protoplanetary disk. Imagine a vast, pancake-shaped cloud of material orbiting a newborn star, composed of countless microscopic dust grains, ice crystals, and gas molecules. In the beginning, this is all there is: a fine, diffuse haze. The journey from these tiny specks to a fully formed, spherical world like Earth is a marathon of cosmic proportions, driven not by violent force, but by gentle, relentless collisions. The initial step is perhaps the most delicate of all. Within the disk, these microscopic dust grains, each smaller than a particle of smoke, begin to bump into one another. In the microgravity environment of the disk, electrostatic forces, a kind of static cling on a miniature scale, cause these grains to stick together upon contact. This isn't a dramatic crash, it's a gentle coalescence forming fragile, fluffy aggregates that resemble intricate fractal snowflakes. Over thousands of years, these fluffy clusters continue to collide and merge, growing slowly from dust motes into pebbles, and then from pebbles into larger rocks. This phase is a gentle snowball effect where the growing objects, now called planetesimals, begin to exert their own tiny gravitational pull. This is the critical turning point. Once an object reaches roughly a kilometer in size, its gravity becomes significant enough to start actively pulling in nearby material, a process known as runaway growth. The planetesimal is no longer just a passive collector. It has become a gravitational predator, clearing its orbital path by drawing in smaller rocks and dust. This stage accelerates the growth dramatically, with these kilometer-sized bodies acting as the planetary building blocks, or embryos, that will eventually merge to form the cores of future planets. The timescales involved in this accretion process are humbling. To go from microscopic dust to a Mars-sized planetary core can take anywhere from 1 to 10 million years. Think about that span of time in the context of our own world. 1 million years ago on Earth, the earliest human ancestors were just beginning to walk upright. The entire timeline of human civilization fits into a mere 10,000 years, a literal blink of an eye compared to the multi-million-year construction project required to form a single planet. This slow, methodical assembly stands in stark contrast to the violent, high-speed events we often associate with the cosmos. A supernova shockwave travels at 10% of the speed of light, reshaping a region of space in a matter of days. A hypervelocity star is flung across the galaxy in a single, rapid slingshot maneuver. But planet formation is a different kind of power, the power of relentless, patient accumulation. It's the cosmic equivalent of building a mountain 1 grain of sand at a time, a testament to the fact that not all of the universe's most important work happens in a flash. Some of it requires an eon of quiet, persistent effort. This gradual process also explains the stunning diversity of planetary systems we observe. The initial conditions of the protoplanetary disk, its total mass, its chemical composition, and its temperature gradient from the hot inner regions to the cold outer reaches dictate the final architecture of the planetary system. Close to the young star, where temperatures are high, only metals and rocky minerals can remain solid. This is why the inner planets in our solar system, like Earth and Mars, are rocky worlds. Their growth was a battle for scarce metallic and silicate material. Farther out, beyond what's called the frost line, temperatures are low enough for volatile compounds like water, ammonia, and methane to freeze into solid ice. This provides a much more abundant supply of building material. Here, planetary cores could grow rapidly, accreting not just rock but massive amounts of ice. Once these cores grew to be about 10 times the mass of Earth, their gravity became strong enough to capture and hold onto the vast reservoirs of hydrogen and helium gas that made up the bulk of the protoplanetary disk. This is how the gas giants like Jupiter and Saturn were born, through a final, rapid phase of gas accretion onto a massive, previously assembled core. The entire structure of our solar system, with its small, rocky inner planets and its giant, gaseous outer worlds, is a direct fossil record of that slow, multi-million-year accretion process within the Sun's infancy disk. It is a permanent reminder that the worlds we see today are the culmination of a patient, cosmic construction project that began with the gentlest of touches between tiny grains of dust. After exploring the natural cosmic accelerators that launch particles at nearly the speed of light, it's awe-inspiring to realize that we have built our own version of these extreme machines right here on Earth. Nestled in a circular tunnel 100 meters beneath the French-Swiss border lies the pinnacle of human engineering and curiosity, the Large Hadron Collider, or LHC. This 27-kilometer-long ring is the most powerful particle accelerator ever constructed, and its primary task is to hurl the tiniest components of matter, protons, to velocities that brush against the universe's ultimate speed limit. Within its supercooled, superconducting magnets, protons are accelerated to an astonishing 99.9999991% of the speed of light. To grasp the precision of that number, consider that at this velocity, a proton is traveling only about 3 meters per second slower than light itself. If a proton in the LHC were racing a photon in a sprint across the entire solar system, the photon would win by less than the length of a car. This isn't just fast, it is the absolute bleeding edge of what is possible for matter with any mass at all. Achieving such an extreme velocity requires an undertaking of almost unimaginable scale and energy. The journey of a single proton in the LHC is not a simple launch, it's a carefully orchestrated cosmic steeplechase. It begins in a simple bottle of hydrogen gas, atoms are stripped of their electrons, and the lone protons are injected into a series of smaller accelerators, each one acting like a booster rocket, pushing the protons faster and faster. Finally, they are fed into the main 27-kilometer ring, where they are gathered into two beams traveling in opposite directions. The vacuum inside the beam pipe is more empty than interplanetary space, a necessity to prevent the protons from colliding with stray air molecules. To bend these near-light-speed beams into a circle, the LHC uses over 1,600 superconducting electromagnets, chilled to a temperature of -271 degrees Celsius colder than the void between galaxies. This intense cold allows the magnets to conduct electricity without any resistance, generating immense magnetic fields that guide the protons. The energy required to accelerate a handful of protons to this velocity is monumental. The entire LHC complex consumes about as much electricity as a large city when it's operating. All of this immense technological effort is focused on a single, fleeting moment, a head-on collision. When these two beams of protons, each carrying the energy of a freight train traveling at 150 kilometers per hour, are steered into a direct collision, the result is a microscopic fireball of pure energy. For an instant, the kinetic energy of the protons is transformed, recreating temperatures and densities not seen since the first trillionth of a second after the Big Bang. In this primordial fury, the very laws of physics as we know them are rewritten, and exotic particles that haven't roamed freely through the universe for over 13 billion years are brought back into brief existence. Our most fundamental understanding of the universe is encapsulated in a theoretical framework called the Standard Model of Particle Physics, which catalogues the known elementary particles and the forces that govern them, with the notable exception of gravity. For decades, a crucial piece of this model was missing, the Higgs boson. This particle is not like a tiny billiard ball. It is better understood as a manifestation of an invisible energy field that pervades all of space, the Higgs field. Just as a celebrity moving through a crowd slows down due to the people clustering around them, particles moving through the Higgs field acquire mass by interacting with it. The more a particle interacts with this field, the heavier it is. Without the Higgs field, electrons would have no mass, atoms could not form, and the universe as we know it would not exist. The discovery of the Higgs boson at the LHC in 2012 was a historic triumph, confirming a prediction made almost 50 years earlier and completing the Standard Model as it stands. But the work of the LHC is far from over. It is now pushing into even more extreme territories, searching for particles that could constitute the mysterious dark matter that fills the cosmos, investigating the reason for the overwhelming dominance of matter over antimatter in our universe, and even probing the possibility of extraspatial dimensions. Every time protons are smashed together at these relativistic speeds, we are, in a very real sense, turning back the cosmic clock and staring directly into the forge where the fundamental rules of our reality were first stamped into existence. But for all the grand journeys we've charted across the cosmos, from the frantic spin of subatomic particles to the slow drift of continents, there is a more intimate kind of motion happening right over our heads every single night. If you were to step outside and gaze up at the familiar constellations, the steadfast Orion, the majestic Ursa Major, they would appear as fixed and unchanging as they did for the ancient Egyptians or the first astronomers of Babylon. This perceived stillness, however, is one of the most profound illusions in astronomy. The stars are not pinned to a celestial sphere, they are all in motion, each traveling on its own unique path through the galaxy. From our earthly vantage point, this creates a subtle, almost imperceptible dance known as proper motion. The slow, gradual shift of a star's position on the sky relative to the more distant stellar background. It is the transverse component of a star's true velocity, the part of its movement that is perpendicular to our line of sight. To witness this cosmic drift, you need a clock calibrated not for human lifetimes, but for the patient rhythms of the galaxy itself. The changes are so minute that they require precise telescopic measurements taken over decades or even centuries to become apparent. The reigning champion of this stellar marathon is a faint red dwarf known as Barnard's star. Located just under 6 light-years away, it is the second closest stellar system to our own Sun, and its proximity gives it a distinct advantage in this race. Barnard's star is hurtling through space at a remarkable velocity relative to us, and as a result, it exhibits the largest known proper motion of any star in our sky. Its progress is a relentless crawl, moving at a rate of about 10.3 arcseconds per year. While that sounds incredibly small, and it is, the cumulative effect over a human timescale is just barely perceptible. To visualize this, imagine the apparent width of the full moon in the sky. It takes Barnard's star approximately 180 years to travel a distance equal to that lunar diameter. This means that since the time of the American Civil War, this star has shifted its position by an amount you could just cover with your thumb held at arm's length. While no single person can witness this journey in their lifetime, by comparing photographic plates taken a century apart, astronomers can create a time-lapse that shows this faint star scuttling purposefully against the fixed backdrop of far more distant suns, a silent testament to the dynamism of our local cosmic neighborhood. So, what propels a star like Barnard's star on such a determined path? This motion isn't a random drift. It is a direct reflection of the complex gravitational ballet and the individual orbits of stars within the Milky Way. Our galaxy is not a rigid structure. Stars orbit the galactic center at different speeds and on slightly different planes, each following its own path dictated by the gravitational pull of the entire galactic mass. Barnard's star is what astronomers call a high-velocity star, and it is moving rapidly relative to our Sun because its galactic orbit is more elliptical and tilted compared to our own. It's as if our solar system is driving on a relatively circular highway lane, while Barnard's star is on a steeply inclined, elliptical overpass, crossing our path at a much higher relative speed. By meticulously mapping the proper motions of thousands upon thousands of stars, astronomers can begin to reconstruct this grand orbital dance. We can identify stellar streams, groups of stars moving together that are the remnants of dwarf galaxies consumed by the Milky Way in the distant past. We can trace the motions of star clusters and even infer the presence of unseen structures through the subtle gravitational tugs they exert on the stars we can observe. This painstaking work, begun with simple telescopes and now supercharged by space observatories like Gaia, which has measured the precise positions and motions of over 1 billion stars, is allowing us to create a dynamic, three-dimensional movie of our galaxy's evolution. We are no longer looking at a static snapshot. We are beginning to see the Milky Way as a living, breathing, and rotating entity, with stars weaving intricate paths around each other in a slow-motion performance that has been running for billions of years. After witnessing the silent, patient drift of stars across millennia, it's almost startling to realize that the cosmos is not a silent movie. It has a soundtrack, one written in the physics of pressure waves, but the volume and pitch of this cosmic sound are wildly different depending on where you are. The speed at which sound travels is not a universal constant like light speed. It's a local variable entirely dependent on the medium it's moving through. Here on the surface of Earth, in our comfortable blanket of air at room temperature, sound propagates at a familiar 343 meters per second. That's fast enough for you to hear thunder a few seconds after seeing a lightning strike, but it's a snail's pace compared to the velocities we've been exploring. This speed is dictated by the properties of our atmosphere, its density, temperature, and the way its molecules bump into each other to transmit a vibrational wave. But step into the extreme environments of space, and the very definition of sound changes, reaching values that are truly astronomical. To understand why, we need to look at the most alien state of matter in the universe, plasma. The vast, seemingly empty space between the stars is not a perfect vacuum. It is filled with an incredibly thin, searingly hot gas, but this gas is so energetic that its atoms have been torn apart. Electrons have been stripped from their nuclei, creating a soup of free-floating charged particles. This is plasma, and it behaves very differently from the neutral gas in our atmosphere. In this environment, the particles are not just randomly bumping into each other. They are linked by long-range electromagnetic forces, and this changes everything about how a disturbance propagates. The sound speed in a plasma isn't about molecular collisions. It's about how quickly a ripple of pressure can travel through this magnetized, charged soup. In the hot, diffuse plasma of the typical interstellar medium, this speed can be staggering, reaching over 100 kilometers per second. That's hundreds of times faster than sound travels in the air you're breathing right now. A whisper in such an environment would cross the entire United States in less than a minute. Now, let's journey to the opposite extreme, to the very heart of our own planet. The Earth's inner core is a place of almost unimaginable pressure, a solid ball of iron-nickel alloy squeezed by the weight of the entire planet above it. In this environment, the atoms are packed incredibly tightly, and the bonds between them are immensely stiff. When a material is that dense and rigid, vibrations pass through it with breathtaking efficiency. Scientists estimate that the speed of sound traveling through the solid inner core could be as high as 11,000 meters per second. That's over 30 times faster than sound in air. This isn't just a theoretical curiosity. By studying how seismic waves from earthquakes travel through the Earth's interior and change speed as they pass through different layers, geophysicists can actually map the planet's internal structure. The speed of these deep Earth vibrations acts as a diagnostic tool, revealing the temperature, composition, and even the crystal structure of materials we can never hope to visit directly. This concept of a sonic speed becomes critically important when we look at some of the most violent and beautiful structures in the cosmos. The key principle is a phenomenon called a shock wave. Imagine an object or a disturbance moving through a medium, whether it's air, water, or interstellar plasma. If that object is moving slower than the speed of sound in that medium, the pressure waves it creates can race out ahead of it, gently nudging particles out of the way. The medium has time to adjust, but if the object starts moving faster than the local speed of sound, it begins to outrun its own pressure waves. It's like a boat trying to go faster than the waves it produces. The waves can't get out of the way and are forced to pile up into a single, steep, powerful wall of compressed energy directly in front of the object. This wall is a shock wave, and it represents a sudden, discontinuous jump in pressure, density, and temperature. This is precisely what happens in the aftermath of a supernova explosion. We discussed the shock wave blasting outward at 30,000 kilometers per second, but to understand its impact, we must compare that speed to the sonic speed of the surrounding interstellar medium. The supernova blast wave is not just supersonic. It's hypersonic, moving thousands of times faster than the 100 km per second sound speed of the interstellar plasma. As this wall of stellar debris and energy plows into the quiet, cold gas of space, it doesn't gently push it. It slams into it with ferocious, unimaginable force. The gas ahead of the shock has no warning, no time to move aside. It is abruptly hit, compressed, and heated to millions of degrees in an instant. This violent interaction is what forges the gorgeous, intricate filaments we see in supernova remnants like the Cygnus Loop or the Veil Nebula. The shock wave acts like a cosmic snowplow, sweeping up interstellar material and triggering the turbulence and compression that leads to the next generation of star formation. It is the sonic speed of the ambient medium that defines the very structure of this expanding bubble of destruction and creation. Without that universal rule governing how pressure waves travel, the chaotic beauty of a supernova's aftermath would be unrecognizable, a silent, formless cloud instead of the vibrant, structured testament to stellar death that we can observe through our telescopes. Now we return to one of the most fundamental and mind-expanding ideas in all of cosmology, the very engine driving the large-scale motion of the cosmos, the Hubble flow. This isn't about individual galaxies darting around on their own. It's about the stately, relentless recession of the entire cosmic fabric, a concept perfectly captured by Hubble's law. Formulated from the groundbreaking work of Edwin Hubble in the 1920s, this law presents a beautifully simple yet profound relationship. The farther away a galaxy is from us, the faster it appears to be moving away. The velocity of a galaxy's recession is directly proportional to its distance. We express this relationship mathematically with the Hubble constant, a number that represents the current rate of the universe's expansion. Its accepted value is around 70 kilometers per second per megaparsec. Let's unpack what that truly means. A megaparsec is an almost unimaginable unit of distance, equivalent to about 3.26 million light-years. So, for every 3.26 million light-years a galaxy is from us, its speed away from us increases by 70 kilometers every single second. A galaxy 100 megaparsecs away would be receding at a staggering 7,000 kilometers per second. This isn't a gentle drift, it's a headlong flight into the void, a speed that escalates with every new layer of space we observe. The most intuitive way to visualize this is to go back to our trusty analogy of the expanding balloon. Imagine the surface of a partially inflated balloon as representing the entire fabric of our universe. Now take a marker and place several dots on that surface, spacing them out at different intervals. Each dot represents a galaxy. Now begin to blow more air into the balloon, steadily inflating it. As you do, watch what happens to the dots. Crucially, no single dot is the center of the expansion on the surface. Every dot is moving away from every other dot. Now focus on any one dot you choose to call home. You'll notice that a dot very close to you on the rubber only moves a small distance away as the balloon expands. But a dot that was already far from you has a much greater amount of stretching rubber between you and it. In the same amount of time, that distant dot appears to have moved a much greater distance away from your vantage point than the nearby one did. From your perspective on your dot, it seems as though the more distant dots are fleeing from you at a much higher speed, even though every dot is essentially stationary on the rubber and it's the space itself that's growing. This is the precise essence of the Hubble flow. It's not that galaxies are rocketing through a static space. It's that the very space-time between them is stretching, and the more space there is to stretch, the greater the apparent velocity of recession we measure. This realization fundamentally reshapes our understanding of our place in the cosmos. A common misconception is that this means we are at the center of some grand cosmic explosion, with everything fleeing directly from us. But the balloon analogy shows this is a complete illusion. An observer living on any other dot on any other galaxy would see the exact same thing. All the other galaxies would appear to be rushing away from them, with the most distant ones moving the fastest. There is no privileged center to the expansion. The universe is behaving the same way from every single point. This universal recession is the definitive evidence that we live in a dynamic, evolving cosmos, one that has been growing from a hotter, denser state for the past 13.8 billion years. The Hubble flow is the permanent, indelible echo of the Big Bang, a signature written in the redshifted light of every distant galaxy, telling us that the very stage upon which the cosmic drama plays out is still stretching, carrying its actors along for a ride that gets faster and faster the farther out you look. And yet, for all the immense, slow-motion churn of the cosmos, some of its most defining moments unfold with a shocking suddenness, where the very face of a star can transform in the time it takes you to have lunch. This brings us to the breathtaking speed of a star's final performance, the rapid dimming of a supernova. We often picture a supernova as a single, brilliant flash, but the reality is a meticulously timed sequence of events, a light show that plays out with a specific, predictable rhythm. The initial explosion is triggered deep within the star as the core collapses at a quarter of the speed of light. The rebounding shockwave then takes hours or sometimes even days to fight its way out through the dense outer layers of the star. When this shockwave finally punches through the stellar surface and bursts into the vacuum of space, we witness the supernova's first visible act, the shock breakout. This is an incredibly violent and rapid release of energy, a flash of intense ultraviolet and X-ray radiation that can cause the star's brightness to skyrocket in a matter of minutes. For a brief, dazzling moment, the dying star can outshine its entire host galaxy in this high-energy light, a final, furious scream before the main event begins. Once the initial shock has passed, the supernova enters its most famous phase, the brilliant, sustained glow that we traditionally associate with these cosmic explosions. But the source of this light holds another secret of speed and transformation. The material ejected by the explosion is expanding at tens of thousands of kilometers per second, and it is initially incredibly hot and opaque. As it expands, it thins out and cools, becoming more transparent. It's at this point that a new power source takes over, one born from the very violence of the explosion. During the supernova itself, the intense heat and neutron flux forge a whole new set of heavy elements through rapid nuclear fusion. Among the most important of these is an unstable isotope of nickel, nickel-56. This nickel is radioactive, and it decays with a half-life of about 6 days into cobalt-56, which in turn decays into stable iron-56 with a half-life of 77 days. It is the energy released by this rapid, continuous radioactive decay that powers the supernova's long-lasting light curve, the graph of its brightness over time. The interplay between this radioactive engine and the expanding debris cloud creates a light curve with a distinctive shape that astronomers can read like a cosmic fingerprint. Initially, the brightness is sustained as the expanding cloud remains thick enough to trap the gamma rays produced by the decaying nickel. This creates a plateau of luminosity. But as the cloud continues to expand and thin, it becomes transparent to these gamma rays, allowing them to escape without being converted into visible light. This is when we witness the supernova begin its rapid fade. The decline in brightness is not random. It closely follows the exponential decay curve of the radioactive cobalt. Watching a supernova light curve is like watching a lump of glowing coal slowly cool, except this coal is the size of a solar system, and its cooling is dictated by the immutable, rapid timetable of nuclear physics. The speed of this photometric evolution, the precise way the brightness rises, plateaus, and falls, is one of the most critical tools astronomers have. By matching the observed light curve to theoretical models, they can determine the key properties of the explosion, such as how much nickel was synthesized, the total energy of the blast, and even the original mass of the star that died. A supernova that fades very quickly suggests a relatively small amount of nickel was created, pointing to a lower mass progenitor star. Conversely, a supernova that remains brilliant for many weeks indicates a prodigious production of radioactive nickel, the signature of a truly monstrous star meeting its end. This rapid, predictable dimming is therefore not just an end, but a message, a final data stream from a stellar catastrophe that allows us to reconstruct the life and death of a sun from millions of light years away. Just when you think a solar system is a stable, orderly place with planets settled into their orbits for all time, we discover that some of the largest worlds have been anything but stationary. This brings us to one of the most revolutionary ideas in modern planetary science, the slow, majestic migration of gas giants. The image of Jupiter and Saturn as permanent fixtures in our own solar system is comforting, but for many worlds in the galaxy, their current address is merely a temporary stop on a journey that began millions of years ago. This process, known as planetary migration, reveals that the architecture of a planetary system is not fixed at birth, but is often a dynamic and evolving masterpiece sculpted by gravity over immense timescales. The very existence of a class of planets called hot Jupiters was the first major clue that turned this idea from a fringe theory into a central pillar of our understanding. Astronomers began finding gas giant planets as massive as Jupiter or even larger, orbiting breathtakingly close to their host stars, completing a full orbit in just a few Earth days. This was a profound puzzle. According to traditional formation theories, a gas giant simply cannot form that close to a star. The intense heat and fierce stellar winds in the inner system would prevent the vast amounts of light gas needed to build a giant planet from ever coalescing. They must form much farther out, beyond the system's frost line, where ices can exist, providing the abundant solid material needed to build a massive core quickly. The inescapable conclusion was that these hot Jupiters had to have formed in the cold, outer reaches of their systems, and then somehow moved inward, settling into their current scorching orbits. The primary engine for this grand-scale relocation is a gravitational tug-of-war between the newborn planet and the very disk that gave it birth, the protoplanetary disk. Imagine a young gas giant freshly formed in the outer regions of a vast, swirling disk of gas and dust. This planet isn't just a passive resident, it's a gravitational powerhouse carving its will into the surrounding material. As the planet orbits, its gravity creates spiral density waves in the disk, like the wake of a boat moving through water. These waves are not symmetrical. The interaction is stronger with the material on the side of the planet's orbit that is rotating slightly slower, and weaker with the faster-moving material on the other side. This imbalance creates a net torque, a twisting force that acts on the planet. In the most common scenario, the outer disk exerts a stronger pull, robbing the planet of orbital energy and angular momentum. As the planet loses this energy, it can no longer maintain its wide orbit, and it begins a slow, steady spiral inward toward the star. This is known as Type I or Type Roman II migration, depending on the planet's mass and its ability to clear a gap in the disk. This migration isn't a violent, chaotic fall. It's a stately, controlled descent that can take hundreds of thousands of years, a glacial procession guided by the invisible hand of gravitational physics. The planet's destiny is essentially to be swallowed by its star, a fiery end to a grand journey. But then, what stops this process? Why isn't our own Jupiter a cinder orbiting dangerously close to the Sun? The answer lies in the delicate timing of the solar system's early life. The protoplanetary disk, the fuel for this migration, does not last forever. It is a transient structure, eventually dissipated by the young star's intense radiation and powerful winds. The migration of a planet halts when the disk of gas is gone, removing the mechanism that was driving its movement. In our solar system, Jupiter likely did begin to migrate inward, but the disk dissipated before it could travel very far, leaving it in its current stable orbit. This celestial balancing act explains the incredible diversity of planetary systems we observe. Some systems had disks that dissipated quickly, freezing their planets in place. Others had longer-lived disks, allowing for significant planetary movement, potentially creating tightly packed systems or sending giant worlds on a one-way trip into the stellar furnace. However, the protoplanetary disk is not the only architect of planetary wanderings. A second, even more dramatic mechanism involves the gravitational interplay between multiple giant planets in a single system. When two or more massive worlds orbit a star, their gravitational influences can stir up a long-term instability. Their orbits can gradually become more and more eccentric, stretching from nearly circular to highly elliptical until their paths eventually cross. When this happens, the system experiences a gravitational showdown. In a chaotic dance, the planets can scatter off one another. One planet might be flung inward on a highly elliptical orbit, its path later circularized by tidal forces from the star to become a hot Jupiter. The other planet, in a conservation of momentum, could be slingshotted outward into a much wider, colder orbit, or even ejected from the system entirely to become a rogue planet, doomed to wander the interstellar void forever. This gravitational scattering model provides an elegant explanation for the wide range of planetary orbits we see, from the tightly wound hot Jupiters to the distant, lonely giants on bizarre, tilted paths. Our own solar system may have experienced a milder version of this chaos early in its history, with Jupiter and Saturn migrating and subtly reshaping the entire planetary architecture, their gravitational influence potentially responsible for the small size of Mars and the existence of the asteroid belt. The slow migration of gas giants is thus a testament to the dynamic and often violent adolescence of planetary systems, a period of gravitational negotiation that ultimately decides the final layout of worlds and determines which orbits will be stable enough to potentially nurture life. Now, let's widen our lens from individual galaxies to the most massive gravitationally bound structures in the entire universe, galaxy clusters. These are the true metropolises of the cosmos, containing hundreds or even thousands of galaxies, all swarming within a common pool of superheated gas and dark matter. From a distance, a cluster like the Coma cluster or Virgo cluster might look like a relatively static swarm, a collection of islands floating quietly in a dark sea. But that serenity is an illusion. If you could see the cluster with a sense that perceived velocity, you would witness a scene of controlled chaos, a grand ballet where entire galaxies, each with its hundreds of billions of stars, are whizzing past one another on random trajectories at absolutely staggering speeds. We're talking about velocities that regularly reach 2,000 to 3,000 kilometers per second. To put that into a truly galactic perspective, at that speed, a galaxy could cross the entire expanse of the Milky Way in less than 100,000 years, a mere instant on the cosmic clock. These aren't the ordered, circular orbits of planets around a star. This is a bustling, high-energy environment where galaxies fly about on elongated paths, constantly crisscrossing the cluster's core like a swarm of bees. This chaotic, high-speed dance is known as velocity dispersion, and it holds the key to one of the most profound discoveries in modern cosmology: how to weigh the invisible. The story of how astronomers use this motion to measure mass begins with a simple, powerful principle from physics, the virial theorem. In essence, this theorem provides a way to connect the motions of objects within a system to the gravitational forces that bind them. For a system in a stable, steady state, like a galaxy cluster that has had billions of years to settle down, the theorem states that the total kinetic energy of all the moving parts is balanced by half of the total gravitational potential energy. In plain language, the faster the galaxies inside a cluster are moving, the stronger the gravitational pull must be holding them together. Think of it like a cosmic scale. You can't see the bowl that holds the weight, but you can watch how fast the marbles are rolling around inside it. If the marbles are zipping around at tremendous speeds, you know the bowl must be incredibly deep and steep to prevent them from flying right out. In a galaxy cluster, the marbles are the galaxies themselves, and their incredible velocities tell us that the gravitational bowl they're moving in is one of the most powerful wells in the entire universe. So, astronomers set out to measure this, using the Doppler shift of the light from hundreds of individual galaxies within a cluster. They can calculate each one's speed relative to the cluster's center. They then plot these velocities to find the dispersion, the statistical spread around the average. A cluster with a low velocity dispersion has galaxies moving at relatively similar, sedate speeds, suggesting a shallower gravitational well. But a cluster with a high velocity dispersion, where some galaxies are hurtling toward us while others are racing away at thousands of kilometers per second, points to an immense gravitational force at work. This is where the mystery deepens enormously. When scientists add up all the mass they can actually see in a cluster, the combined mass of all the stars in all the galaxies, plus the incredibly hot, diffuse gas that fills the space between them and glows in X-rays, they get a number. But when they use the velocity dispersion of the galaxies and the virial theorem to calculate the total gravitational mass needed to produce those observed speeds, they get a number that is typically 5 to 10 times larger. The gravity required to whip these galaxies around at such ferocious speeds is far greater than anything the visible matter can account for. This missing mass problem was one of the very first and strongest pieces of evidence for the existence of dark matter. The random, high-speed motions of galaxies are a direct tracer of the immense, invisible halo of dark matter that forms the underlying skeleton of the cluster, a gravitational scaffold that comprises the overwhelming majority of the cluster's total substance. This revelation connects the large-scale structure of the universe directly to its most elusive component. We now understand that galaxy clusters don't form in the regions of space with the most visible galaxies. They form in the regions with the highest concentrations of dark matter. The random motions of the galaxies we can see are like flotsam on the surface of a deep, dark ocean, their frenetic speed betraying the powerful, hidden currents of gravity flowing beneath. Without this dark matter halo providing the extra gravitational glue, the clusters would simply fly apart. The galaxies would escape into the void, their velocities too great to be contained by the puny pull of the stars and gas alone. So, the next time you see an image of a dense galaxy cluster, remember that you are not just looking at a collection of brilliant islands. You are witnessing the outer signature of a deep, dark gravitational dominion, a hidden empire of matter whose presence is felt only through the breathtaking speed of the stars it commands. While we often look to distant galaxies to find extremes of speed, some of the most consequential and violent accelerations occur much closer to home, right on the surface of our own star. The sun may seem like a steady, constant source of light and warmth, but it is a dynamic and temperamental sphere of incandescent plasma, capable of unleashing storms of almost unimaginable ferocity. These storms manifest in two primary and often linked forms, the solar flare and the coronal mass ejection. A solar flare is a sudden, intense flash of brightness that occurs when magnetic energy that has built up in the solar atmosphere is suddenly released. It's a colossal bomb of radiation, primarily in the form of X-rays and extreme ultraviolet light, that explodes outwards at, of course, the speed of light. This flash can be so powerful that, for a few minutes, it can outshine every other source of X-rays in the entire sky, including distant neutron stars and black holes. But while the flash of light is instantaneous, the more physically substantial event often follows just behind it. This is the coronal mass ejection, or CME, and it is one of the most massive and fastest-moving structures our solar system produces. Imagine a colossal bubble, not of air but of magnetized solar plasma, a searing hot gas of charged particles being violently vomited forth from the sun's outer atmosphere, the corona. The scale is almost incomprehensible. A single CME can carry with it billions of tons of solar material, a mass equivalent to a small mountain range, all ripped from the sun's grip and hurled into the void. And the speeds at which this colossal blob of matter travels are what truly define its danger. These ejections can be launched with a staggering range of velocities, from a relatively slow several hundred kilometers per second to truly extreme speeds that can exceed 3,000 kilometers per second. At that maximum velocity, a CME could cross the 150 million kilometer gulf between the Sun and Earth in less than 14 hours, a journey that typically takes light itself just over 8 minutes. But for a physical object of such immense mass, it is a breathtaking relativistic cruise. The journey of a CME from the Sun to the Earth is a race against the solar wind, a race that only the fastest of these events can truly win. As it travels, this immense cloud of magnetized plasma expands, sometimes growing to be larger than the Sun itself by the time it reaches our orbit. And when one of these fast-moving giants is aimed directly at Earth, our planet's magnetic field becomes the first and only line of defense. The collision is not a gentle merging, it is a violent, energetic shock. When the Siamese' own embedded magnetic field slams into Earth's magnetosphere, the protective bubble generated by our planet's molten core, the two magnetic architectures reconfigure in a complex and turbulent dance. This interaction funnels vast quantities of energetic particles down toward the Earth's magnetic poles, where they smash into atoms in the upper atmosphere. It is this spectacular process that creates the aurora borealis and aurora australis, the beautiful northern and southern lights that paint the polar skies with shimmering curtains of green, red, and purple. For centuries, these displays were seen as mysterious and spiritual phenomena. We now know they are the visible signature of our planet weathering a storm from the sun, a beautiful side effect of a potentially destructive event. However, the beautiful auroras are merely the picturesque side of a much more serious threat to our modern, technologically dependent civilization. The same geomagnetic storms that create the lights also induce powerful electrical currents in the ground and in long conductors like power lines, railways, and pipelines. The most famous historical example of this was the Carrington event of 1859. A solar superstorm so powerful that telegraph systems across Europe and North America failed, with operators receiving severe shocks and some telegraph pylons spontaneously bursting into flames from the induced currents. In our hyper-connected 21st century, the consequences of a similar event today would be catastrophic on a global scale. The intense electromagnetic pulses could fry the delicate electronics in satellites, knocking out global positioning, communications, and weather monitoring systems. More terrifyingly, the ground-level currents could overwhelm and permanently damage the massive transformers that form the backbone of our continental power grids. Unlike a local power outage, these transformers are not kept in stock. They are custom-built, multi-million-dollar machines that can take years to replace. A direct hit from a fast, powerful coronal mass ejection could plunge entire nations into a blackout lasting not days, but months or even years, with unimaginable social and economic consequences. This direct link between a cosmic event happening 93 million miles away and the very lights in our homes and the phones in our pockets is a stark and humbling reminder that the speeds we chart in the cosmos are not just abstract numbers for astronomers. They are real, physical forces that can reach out from the heart of our star and touch our world in ways both beautiful and profoundly disruptive. A constant demonstration that we are not separate from the dynamic violence of our solar system, but living right in the middle of it. But even against the backdrop of the sun's violent storms and the stately recession of galaxies, there exists a form of change so profoundly slow and vast that it defines the very thermal history of our universe. This brings us to the ultimate cosmic fossil, the cosmic microwave background radiation. Imagine an echo not of sound but of light and heat, a relic glow that permeates every cubic centimeter of the cosmos. This is the afterglow of the Big Bang itself, the moment when the universe cooled enough for atoms to form and light could finally travel freely across space. That primordial flash, once searingly hot, has been stretched and cooled by the relentless expansion of the universe over the past 13.8 billion years. And we can still detect it today as a faint, cold whisper of microwave radiation bathing the entire sky. The truly mind-bending aspect of this cosmic backdrop isn't just its existence, but its rate of change. The cooling of this radiation is a process of almost unimaginable patience. From a temperature of around 3,000 degrees Kelvin when it first broke free, it has cooled to just 2.7 degrees above absolute zero today. That represents a temperature drop of only about 1 single degree Celsius over the entirety of the universe's 13 billion year history. To put that into a human context, it's a change so gradual that if you could somehow feel this cosmic temperature, your great-great-grandchildren would not perceive it to be any colder than you do today. The universe is not cooling in a rush, it is exhaling its primordial heat with a slowness that utterly dwarfs all human conception of time. This glacial rate of cooling is a direct, observable consequence of the expansion of space. The mechanism is beautifully simple yet profound: cosmological redshift. As the fabric of the universe stretches, it also stretches the wavelength of the light traveling through it. Think of the photon, a particle of light from the Big Bang's glow, as a wave on a rubber sheet. As the sheet is steadily pulled in all directions, the wave crests are pulled farther and farther apart, lengthening its wavelength. In the electromagnetic spectrum, longer wavelengths correspond to lower energy and consequently lower temperature. So, the expansion of space itself acts as a cosmic refrigerator, continuously and gently dialing down the temperature of this background radiation. The relationship is perfectly linear. The temperature of the cosmic microwave background is inversely proportional to the scale of the universe. When the cosmos was half its current size, the background temperature was twice as high as it is now. This provides us with a built-in thermometer for the universe at any point in its past, a direct link to its earlier, hotter, and denser states. The fact that this cooling has amounted to just 1 degree over such an incomprehensible span is a testament to the sheer scale of cosmic expansion. The universe has grown so vast that even this powerful cooling effect is diluted across eons, resulting in a thermal change that is barely perceptible even across timescales that see the birth and death of entire galactic civilizations. The profound stability and near uniformity of this background temperature offer perhaps the strongest evidence we have for the Big Bang theory, but they also hide a deeper story of imperceptible transformation. When we map the cosmic microwave background with exquisitely sensitive instruments like the Planck satellite, we see a sky that is almost perfectly uniform, varying by only about 1 part in 100,000. These tiny fluctuations, these seeds of imperfection, are the blueprints for all the structure we see today. The galaxies, clusters, and superclusters all grew from those minute variations in density. Yet, the overall cooling of this background is a global, relentless process that affects every single one of those seeds equally. It is the ultimate baseline against which all other cosmic change is measured. This incredible slowness forces us to confront a universe whose most fundamental processes operate on a clock that has no analog in our daily lives. We measure our existence in heartbeats and seasons, civilizations in centuries and millennia, but the universe measures its thermal history in units of billions of years per single degree of change. This isn't a universe of sudden, dramatic shifts in its fundamental state, but one of patient, inexorable evolution, a grand cooling trend that will continue until the background radiation fades into an insignificance so profound that future cosmologists, if any exist, might not even be able to detect it at all. While hypervelocity stars are the cosmic cannonballs flung from the galactic center, there's another class of stellar speedster born from much more localized, yet equally dramatic celestial drama. These are the runaway stars, and their story unfolds not in the shadow of a supermassive black hole, but within the turbulent and crowded nurseries where stars are first born. Imagine a bustling stellar metropolis, a young, dense open cluster teeming with hot, massive, and brilliantly blue stars. In such a packed environment, gravitational close encounters are not just possible, they're inevitable. The most common origin story for a runaway star is a violent gravitational slingshot within a multiple star system. Picture a tight binary pair, 2 stars orbiting one another, when a third, more massive star intrudes on their dance. The resulting 3-body interaction is a gravitational tug-of-war that often ends with one of the stars being unceremoniously ejected, catapulted away at a tremendous speed, while the other 2 stars form a new, tighter binary or are sent careening off in other directions. It's a stellar game of billiards on a cosmic scale where the cue ball is another sun, and the payoff is a star sent flying into the void. these runaway stars are not quite as fast as their hypervelocity cousins from the galactic center, but their speeds are still breathtaking, typically ranging from 30 to over 100 kilometers per second. At that pace, they are true interstellar travelers, destined to leave their birthplace far behind and spend their lives as stellar nomads, crossing the vast, empty tracks between the spiral arms of our galaxy. Their journey, however, is rarely a silent one. As they race through the galaxy, they carry with them the immense power of their own stellar winds. This is a continuous, supersonic outflow of particles blowing from the star's surface, a common feature of hot, massive stars. When this rapidly moving stellar wind slams into the nearly stationary, thin gas of the interstellar medium, it creates a phenomenon as beautiful as it is revealing, a bow shock. Think of a speedboat racing across a calm lake. The boat pushes the water aside, creating a V-shaped wave that spreads out in front of its bow. A runaway star does the exact same thing, but in the intangible water of interstellar space. The collision between the supersonic stellar wind and the ambient gas compresses and heats the material, causing it to glow, often in the infrared part of the spectrum. The result is a vast, arcing wall of luminous gas, a cosmic wave that always stands ahead of the star, precisely marking its direction of travel. These bow shocks are not just beautiful, they are functional, acting as a kind of interstellar headlight that illuminates the star's path. Because the runaway star itself is often obscured by the very dust it's plowing through, the bow shock can be the primary way we detect its presence and measure its incredible speed. Telescopes like NASA's Spitzer Space Telescope and the Wide Field Infrared Survey Explorer have catalogued dozens of these stunning structures, each one a perfect parabolic arc telling the story of a star on the run. Some of these runaways have even more violent origin stories. A second compelling mechanism for their creation involves the death of a companion star in a supernova explosion. In a tight binary system, if one of the stars is massive enough to go supernova, the explosion can be profoundly asymmetric. The sudden, catastrophic loss of mass effectively disappears one half of the binary partnership, instantly severing the gravitational bond. The remaining star, now abruptly freed, is flung away with whatever velocity it had at the moment of the explosion, like a ball on a string when the string is suddenly cut. This can give the star a tremendous kick, sending it racing across the galaxy as a surviving witness to a stellar catastrophe. In some dramatic cases, astronomers can even trace the path of a runaway star backward across the sky to a supernova remnant, finding the ghost of the explosion that set it loose. Whether through gravitational billiards or a supernova kick, these high-velocity runaways are a testament to the dynamic and often chaotic nature of star clusters, proving that even the act of stellar birth can be a turbulent process that sends some of its children out into the galaxy at astonishing speeds. This 8-minute and 20-second journey for sunlight is more than just a travel time. It is the most personal and immediate example of a fundamental principle that governs our entire view of the cosmos, a concept called look-back time. We are not seeing the sun as it is in this very moment. We are seeing it as it was over 8 minutes in the past. If a colossal solar flare were to erupt on the sun's surface and instantly vaporize it into a cloud of plasma, a physically impossible but illustrative scenario, we on Earth would continue to orbit normally and bask in its light, completely unaware of our star's demise for those entire 8 minutes and 20 seconds. Our reality is quite literally on an informational time delay. Now, take this concept and stretch it across the unimaginable gulfs of interstellar space. The nearest star system to our own, Alpha Centauri, is about 4.3 light-years away. When you gaze up at that tiny point of light, you are not seeing it tonight. You are witnessing photons that left the surface of that star around the time early humans were first mastering the use of stone tools. You are looking over 4 years into the past. The principle scales up to a truly breathtaking degree. The brilliant star Betelgeuse in the constellation Orion is roughly 500 light-years distant. The light hitting your eye tonight began its journey around the year 1524 during the height of the Renaissance in Europe. When astronomers point their telescopes at the majestic Andromeda galaxy, the nearest major spiral galaxy to our own, they see it as it was 2.5 million years ago, a time when early hominins were first walking the plains of Africa. The photons striking their detectors left Andromeda long before modern humans even existed. This transforms our night sky from a simple picture into a layered historical document. Every star, every galaxy is frozen at a different point in its own history, a celestial museum where the exhibits are not arranged by theme, but by the immutable speed of light. We can never know what these objects look like now, because now is a local concept. The universe's stubborn refusal to allow any information to travel faster than light ensures that we are forever looking backward in time, peering into an ever deeper past the farther out we look. This isn't a limitation of our technology, it is a fundamental feature of the cosmos, a rule written into the fabric of space-time that makes every act of stargazing a form of time travel. Yet for all the dramatic, high-speed collisions that can reshape two galaxies in a cosmic heartbeat, the vast majority of a galaxy's life is not spent in these brief, violent encounters. Instead, it undergoes a profound and continuous transformation on a timescale of almost unimaginable patience, a process astronomers call secular evolution. This is the slow, internal dance of a galaxy, the gradual churning of its stars, gas, and dust that alters its very essence over billions of years, a quiet but relentless reinvention that operates on a clock calibrated for eons. While a galactic merger is a spectacular, fiery sprint, secular evolution is the ultimate marathon, a steady, persistent force that writes the final chapters of a galaxy's story long after the fireworks of its youth have faded. It's the difference between a sudden, catastrophic earthquake that reshapes a landscape in minutes and the slow, persistent creep of tectonic plates that builds entire mountain ranges over millions of years. Both are powerful, but one is a fleeting event, while the other is the enduring background process that truly defines the long-term character of the terrain. One of the most captivating manifestations of this slow evolution is the formation of a galactic bar. If you look at images of spiral galaxies, you'll notice that many, including our own Milky Way, feature a bright, elongated structure of stars cutting directly through their center, a stellar bar. This isn't a permanent, rigid feature. It's a dynamic, rotating pattern that emerges naturally from the gravitational interactions within the galaxy's disk. Think of the galaxy not as a solid object, but as a vast collection of stars on slightly different orbits, all tugging on one another as they go around. This collective gravitational pull can cause orbits to become more elongated over time, and these elongated orbits can align, reinforcing each other to create a coherent, bar-shaped structure that rotates as a single unit. The formation of a bar is not an instant process. It unfolds over hundreds of millions of years, a slow gravitational settlement that organizes the galaxy's central regions. Once established, this bar becomes a powerful engine for internal change. As it rotates, its gravitational field acts like a giant cosmic spoon, stirring the galaxy's inner pot. It can funnel vast amounts of gas and dust from the outer spiral arms inward toward the galactic center. This inflow of fresh, cold gas can trigger intense bursts of star formation in the central regions, creating what's known as a nuclear star cluster. Even more significantly, this relentless fueling can provide a feast for the supermassive black hole lurking at the very heart of the galaxy, potentially awakening it from its slumber and turning the galaxy into a brilliant active galactic nucleus or quasar. The bar, born from slow internal dynamics, becomes the primary architect of the galaxy's central ecosystem, dictating the pace of star birth and the activity of its central monster for billions of years. But secular evolution also has a quieter, more somber side, one that leads to the gradual slowing of a galaxy's vibrant star-forming life. This process is known as quenching, and it represents the transition of a galaxy from a blue, gas-rich, star-forming spiral into a red, gas-poor, quiescent elliptical. The causes of quenching are varied and work in concert over immense timescales. One primary mechanism is simply the exhaustion of fuel. A galaxy is born with a finite reservoir of cold gas, the raw material for new stars. As generations of stars are born, live, and die, a significant amount of this gas gets locked away. Massive stars die in supernova, but lower mass stars like our Sun live for billions of years, effectively sequestering their mass for eons. Furthermore, when stars die, they often return some enriched gas to the galaxy, but supernova explosions can also heat the surrounding gas to such high temperatures that it becomes too energetic to collapse and form new stars. This process, known as virial heating, slowly raises the temperature of the galaxy's gas reservoir, making it increasingly difficult for new stellar nurseries to coalesce. Another critical factor is the environment surrounding the galaxy. For galaxies living in the crowded core of a galaxy cluster, a brutal process called ram pressure stripping can efficiently remove their star-forming fuel. As a spiral galaxy plunges through the cluster at thousands of kilometers per second, it rams into the incredibly hot, thin plasma that permeates the space between galaxies. This intracluster medium acts like a ferocious cosmic wind, and its pressure can be so intense that it literally blows the cold gas right out of the galaxy's disk, like leaves being stripped from a tree in a hurricane. Once this gas is gone, the galaxy's ability to form new stars is effectively strangled. Its existing massive blue stars will quickly burn out, leaving behind the longer-lived, cooler, redder stars. Over a few billion years, the galaxy's color will shift dramatically from blue to red, and its spiral structure, which requires ongoing star formation to maintain its bright blue arms, will slowly fade and blur. The galaxy doesn't die, it simply enters a long, quiet retirement, its stellar population aging in unison, its brilliant star-forming factories shut down permanently. This slow quenching is one of the most significant transformations a galaxy can undergo, and it's a process driven not by a single cataclysm, but by the cumulative effect of its own internal life cycle and its gentle, persistent interactions with its environment over timescales that span the age of the universe itself. The vibrant, star-forming galaxy we see today may be the quiet, red relic of tomorrow, its dramatic change orchestrated not in a flash but in a slow, relentless whisper. But the universe has a wonderful way of repeating its most spectacular patterns across every imaginable scale, offering us a front-row seat to phenomena we could otherwise only witness from billions of light years away. This brings us to the incredible world of microquasars. If the relativistic jets from active galactic nuclei are the universe's ultimate fireworks display, then microquasars are the brilliant desktop model version, operating right here in our own cosmic backyard. These systems take the mind-bending physics of a supermassive black hole and shrink it down to a stellar mass scale, creating a nearby laboratory where we can watch the violent dance of accretion and ejection unfold in fast forward. A microquasar is essentially a binary star system with a truly extreme personality. It consists of a normal hydrogen-fusing star like our Sun, locked in a tight orbital dance with a vampiric companion, either a stellar mass black hole or a neutron star. The sheer proximity of these two objects is the key to the entire spectacle. The immense gravity of the dense remnant relentlessly pulls streams of gas from the outer layers of its stellar companion. This stolen material doesn't fall straight in. It spirals inward, forming a searingly hot, glowing accretion disk around the black hole or neutron star, a miniature version of the vast disks that feed the monsters at the centers of galaxies. It is from this scaled-down maelstrom that the microquasar earns its name. Just like its gigantic cousins, the system can launch twin jets of plasma perpendicular to the plane of the accretion disk at velocities that are a significant fraction of the speed of light. We're talking about outflows that have been measured reaching 80 to 99% of light speed. The sheer power required to accelerate matter to such velocities around an object only a few times the mass of our Sun is staggering. The energy comes from the immense gravitational potential of the infalling material and the furious dynamics of the accretion disk itself, with magnetic fields acting as the slingshot that collimates and focuses the plasma into those narrow, piercing beams. While these jets are minuscule compared to their extragalactic counterparts stretching for light years instead of hundreds of thousands of light years, their relative proximity to Earth, often within our own galaxy, allows us to study their structure and behavior with a level of detail that is simply impossible for distant quasars. We can watch their brightness flicker and change over days, weeks, or months, rather than the millennia it takes for signals to reach us from active galaxies. This rapid timescale turns the microquasar into a real-time physics experiment, allowing astronomers to directly test theories about how jets are born, how they are fueled, and what happens when they slam into the surrounding interstellar medium. One of the most profound insights from studying microquasars is the revelation of scale invariance. The physics governing the launch of a jet from a stellar mass black hole appears to be fundamentally the same as that governing a jet from a supermassive black hole a billion times more massive. The same processes of accretion, angular momentum conservation, and magnetic field amplification seem to work identically, regardless of the size of the central engine. This is a powerful unifying principle in astrophysics. It suggests that if you understand the mechanics of a microquasar, you are, in essence, understanding the core mechanics of the most luminous objects in the universe. These nearby systems allow us to see the intricate connection between the accretion disk and the jet in action. Observations have shown that the jet often switches on during a specific state of the accretion disk when it becomes very hot and bright. We can see material vanish from the inner disk and almost simultaneously reappear as a bright knot of plasma shooting down the jet, a direct transfer of mass and energy that we can track as it happens. The value of these celestial laboratories was brilliantly demonstrated by a famous microquasar within our own galaxy known as JRS 1915+105, or simply JRS 1915. In 1994, astronomers observed this system undergo a massive outburst. As the black hole began to feed ravenously on its companion star, it launched a brilliant jet. Using the sharp radio vision of telescopes across the globe working in unison, a technique known as very long baseline interferometry, scientists were able to actually measure the apparent motion of blobs of plasma in this jet. The results were astonishing. The blobs appeared to be moving at 20 times the speed of light. This superluminal motion is actually a breathtaking relativistic illusion. It occurs when a jet of material is pointed very nearly along our line of sight and is traveling at a significant fraction of light speed. The jet is almost keeping pace with the very light it emits. Imagine a photon and a blob of plasma in a race toward Earth. The blob is traveling so fast that the light it emits from a point slightly closer to us has almost no head start. This compresses the time between the arrival of light from different positions, creating the illusion that the blob is moving across the sky faster than light. This observation wasn't just a neat trick, it was direct quantitative proof of the relativistic nature of the jets, confirming that the physics of Einstein's special relativity was at play in these stellar systems. By studying the exact speed and angle of these superluminal motions, astronomers could precisely calculate the true intrinsic velocity of the jet material, confirming that it was indeed a cosmic bullet traveling at over 90% of the universal speed limit. Microquasars, therefore, are far more than just miniature curiosities. They are the essential bridges in our understanding, connecting the small-scale violence within our galaxy to the large-scale architecture of the entire cosmos, proving that the universe often writes its most important rules in a language that repeats from the smallest stage to the largest. But even as our sun carries us on its grand orbit and our solar system sails through the local interstellar cloud, we are part of an even larger and more profound motion. Our entire Milky Way galaxy, a colossal pinwheel of hundreds of billions of stars, is itself on a collision course. Right now, our galactic home is hurtling through the void of the local group, our small galactic neighborhood toward the Andromeda galaxy at a breathtaking velocity of about 110 kilometers every second. To visualize that speed, imagine traversing the entire distance from the Earth to the Moon in less than an hour. This isn't a gentle drift, it's a headlong rush toward a destiny that will utterly reshape our night sky and the very structure of our galaxy, an inevitable cosmic merger set to occur in about 4.5 billion years. This future event, often dramatically called a collision, is perhaps better understood as a slow-motion, gravitational dance of immense grace and complexity. The two galaxies are not on a direct impact trajectory like two billiard balls. Instead, they are drawn together by their mutual gravitational pull, and their first close pass will be more of a graceful swing by than a head-on crash. Given the vast distances between individual stars within each galaxy, it's incredibly unlikely that any two stars will physically collide. The interstellar space is just too empty. However, the galaxies themselves, their structures of stars, gas, and dust, will not emerge unscathed. During that first close encounter, the immense tidal forces, the gravitational tug of war between the two behemoths, will wreak havoc. These forces will stretch and warp the elegant spiral arms of both the Milky Way and Andromeda, pulling long, brilliant streams of stars out into the void like cosmic taffy being pulled apart. The serene disk of our galaxy will be violently distorted, its familiar shape lost forever in a spectacular display of gravitational sculpting. After this first dramatic pass, the two galaxies will swing apart, only to be pulled back together by their unwavering gravitational embrace. They will fall toward each other again and again, their orbits decaying with each passage. Over the course of 1 to 2 billion years, this repeated gravitational interaction will slowly bleed away their orbital energy, and they will settle into a single, new and larger galaxy. Computer simulations of this process paint a stunningly beautiful picture. The two spiral structures will be completely blended and erased, their stars randomized into a more elliptical, football-shaped configuration. The new galaxy, often nicknamed Milkdromeda, will be a giant elliptical galaxy, a testament to the merger that created it. This isn't just a theoretical prediction. We see this same process playing out all across the universe. The Hubble Space Telescope has captured countless images of galaxies in various stages of merger, their forms twisted into strange rings, tidal tails, and chaotic swirls of light, providing us with a cosmic photo album of our own distant future. For any hypothetical future inhabitants of Earth, or whatever world might harbor life at that time, the view from the surface would be truly transformational. As the merger progresses, the Andromeda galaxy, which today appears as a faint, fuzzy smudge in the constellation of the same name, would grow steadily brighter and larger in the night sky. Eventually, it would fill a significant portion of the heavens, its spiral arms and bright core a dazzling, terrifying, and beautiful sight. The familiar constellations of our Milky Way would be scrambled beyond recognition as new patterns of stars from Andromeda are woven into the celestial tapestry. While the direct risk to planetary systems from stellar collisions is minuscule, the increased gravitational nudges could potentially fling some stars into new, unpredictable orbits, and the influx of dense gas clouds could trigger intense, widespread waves of new star formation, lighting up the galaxy with the blue-white glow of newborn stellar nurseries. This grand cosmic event reminds us that galaxies are not static islands, but dynamic, evolving entities, constantly interacting and merging in a cycle of creation and destruction that has been ongoing since the universe began. Our Milky Way's current journey toward Andromeda is just one chapter in this endless story, a future-oriented perspective that grounds our present location in the cosmos within a narrative of perpetual, majestic change. But to truly grasp the environment that creates these relativistic jets and powers quasars, we need to listen to the frantic, high-frequency heartbeat of the system itself, a pulse that comes not from the jet, but from the chaotic inner sanctum of the accretion disk. While the overall structure of the disk may appear stable over long periods, its innermost regions, the final few hundred kilometers before matter vanishes forever, are a seething, tempestuous maelstrom. Here, in this zone of unimaginable gravity and friction, the disk doesn't glow with a steady light. It flickers, strobe-like, with rapid, unpredictable changes in brightness that can occur in the blink of an eye, sometimes on timescales as short as milliseconds. This isn't a gentle twinkling, it's a violent, high-speed stutter in the light output, a direct signal from the edge of the abyss. The origin of this rapid flickering lies in the fundamental nature of the accretion disk itself, which is not a smooth, homogeneous river of gas, but a turbulent and magnetized plasma. Two primary, interconnected processes are responsible for this chaotic light show. The first is the sheer, raw turbulence generated by the differential rotation of the disk. Material closer to the black hole orbits at a much higher velocity than material just a bit farther out. This creates immense shear forces, like two sheets of sandpaper grinding against each other at relativistic speeds. This friction doesn't just generate heat, it churns the plasma into a frothing sea of vortices and eddies. Denser, hotter clumps of plasma can form and dissipate in an instant, each one glowing brightly before being torn apart, contributing to the rapid, random fluctuations in the overall brightness we observe. The second, and even more energetic, driver of this flickering is a process known as magnetic reconnection. The swirling, ionized plasma of the disk is threaded with powerful magnetic fields. As the disk churns, these field lines are stretched, twisted, and wound up like immensely powerful rubber bands. Eventually, the stress becomes too great, and the field lines can suddenly snap, breaking and reconnecting in a new, lower energy configuration. This event, a magnetic reconnection, is like a colossal short circuit in the plasma. It releases a tremendous amount of stored magnetic energy in a sudden, explosive burst, accelerating particles to near light speeds and producing a brilliant, localized flash of radiation. Think of it as a miniature solar flare, but occurring in an environment far more extreme than the surface of our Sun, and happening not just once, but in thousands of locations throughout the inner disk simultaneously and at random. It's a continuous fireworks display of magnetic explosions, each one contributing a tiny, sharp spike to the overall flickering signal we detect from Earth. This rapid flickering is far more than just a visual curiosity. It is an incredibly powerful diagnostic tool for astronomers. The key insight lies in a principle of physics. No signal, not even a fluctuation in light, can travel faster than light itself. This means that the timescale of the flickering places a strict upper limit on the physical size of the region producing it. If we see the brightness of an accretion disk change significantly over, say, 1 millisecond, then the source of that variation cannot be larger than the distance light can travel in 1 millisecond, which is about 300 kilometers. This simple fact allows us to effectively probe the very heart of the accretion process. By analyzing the fastest flickers, we can effectively measure the size of the innermost stable orbit around the black hole, a region where the laws of general relativity dominate and spacetime itself is dragged around the spinning singularity. The presence of extremely rapid millisecond flickering is a strong indicator that we are seeing emission generated from the very precipice of the event horizon, a place where the orbital period of matter is itself only a few milliseconds. By studying not just the speed but also the specific patterns and frequencies within this flickering light, astronomers can perform a kind of cosmic seismology. Different types of instabilities produce different characteristic signals in the light curve. It's like listening to the engine of a distant car. A trained mechanic can distinguish a well-tuned hum from the irregular sputter of a misfire. In the same way, by meticulously dissecting the flickering signal from an accretion disk, scientists can distinguish between turbulence-driven fluctuations and the sharper spikes from magnetic reconnection events. They can even detect quasi-periodic oscillations, which are semi-regular flickers that may correspond to the orbital frequency of blobs of hot plasma at specific radii in the disk. This allows them to map the structure and dynamics of the accretion flow itself, probing the effects of the black hole's immense gravity on the surrounding space-time in a way that would be impossible with a steady, unchanging light source. The frantic millisecond flicker of the accretion disk is therefore a coded message, a high-speed data stream arriving directly from one of the most violent environments in the universe, allowing us to understand the fundamental physics governing matter in its final moments before it is lost from our view forever. Now, let's turn our attention to a more intimate and gradual kind of cosmic motion, one that doesn't involve violent explosions or high-speed jets, but a gentle, persistent tug that can completely redefine a world over billions of years. This is the slow and inevitable process of tidal locking, a gravitational dance that results in a celestial body always showing the same face to its partner, much like our own moon does with the Earth. The mechanism behind this cosmic synchronization is the same force that gives us ocean tides, but its long-term effects are far more profound than the daily ebb and flow of the sea. It all begins with gravity's uneven pull. A planet or moon is not a perfectly rigid sphere, it has some flexibility. The gravitational pull from its partner is stronger on the side that is closer and weaker on the far side. This difference in force stretches the object slightly, creating two subtle bulges, one facing its partner and one on the opposite side. Think of it as gently squeezing a soft rubber ball between your thumb and forefinger. It bulges out at both pressure points. Now imagine this flexible, bulging object is also rotating on its own axis. As it turns, it tries to carry these gravitational bulges with it, but the bulges want to stay aligned directly with the gravitational source. This creates a constant, internal friction as the object's rotation tries to drag the bulges out of alignment, and gravity tirelessly pulls them back. This friction acts as a brake, an endless source of drag that very, very slowly saps the object's rotational energy. The process is unbelievably gentle, but over cosmic timescales it is relentless. The rotation gradually slows down until the object completes one full spin on its axis in exactly the same time it takes to complete one full orbit around its partner. At this point, the bulges are perfectly aligned, the gravitational tug is balanced, and the friction ceases. The object is now tidally locked, forever presenting one hemisphere to its companion, while the other side is condemned to perpetual outward-facing darkness. Our moon is the most familiar and completed example of this process. Billions of years ago, the moon likely rotated much faster, and Earth would have seen all of its sides. But the Earth's gravity, being so much stronger, applied its tidal brakes efficiently, and the moon's rotation slowed until it reached its current synchronized state. This is why we only ever see one face of our lunar neighbor. The timescales for this process are as vast as the solar system itself. For the moon, it likely took only a few tens of millions of years to become locked, a relatively quick process in geological terms due to its proximity to Earth and its relatively small size. But for other systems, it can take far longer. The process depends critically on the distance between the two bodies and their relative sizes. Worlds that are very close to their host star or planet feel a much stronger tidal force and can become locked within a few billion years. Those that are farther out may never achieve perfect locking within the entire lifetime of their star. This is why we see such a diversity of rotational states in our own solar system. Many of the moons orbiting Jupiter and Saturn are tidally locked to their giant planetary parents, but the planets themselves are not locked to the Sun because the distances are too great and the timescales required are longer than the current age of the solar system. This leads us to one of the most exciting implications of tidal locking in the search for life beyond Earth: the prevalence of tidally locked exoplanets. A huge number of the rocky planets discovered orbiting red dwarf stars, the most common stars in the galaxy, are thought to be tidally locked. Because these stars are so faint and cool, their habitable zone where liquid water could exist is located very close in. At such short distances, the tidal forces are immense and locking happens quickly. This creates a world of stark and permanent contrasts. One hemisphere is locked in eternal, scorching daylight, permanently facing the star. The other hemisphere is in eternal, frigid night, forever turned away. This sounds like a recipe for a lifeless world, with one side boiled away and the other frozen solid. But nature often finds a balance. Many climate models suggest that a thick enough atmosphere could circulate heat from the day side to the night side, potentially creating a thin, temperate band right along the terminator line, the razor's edge between perpetual day and eternal night. On such a world, the sun would never rise or set. It would hang motionless in the sky, a fixed beacon of heat and light. Life, if it existed, would be confined to a perpetual twilight ring, with the landscape dominated by constant, powerful winds howling from the hot side to the cold side in a desperate attempt to equalize the extreme temperature difference. The slow, patient process of tidal locking doesn't just change a world's rotation. It fundamentally engineers its entire climate, its weather patterns, and the very potential for life to take hold, creating environments that are alien beyond anything we experience in our own solar system. Of all the ghostly travelers in the cosmos, none are more pervasive or elusive than the neutrino. Born from the nuclear furnaces at the heart of stars and the cataclysmic violence of supernova, these subatomic phantoms are the universe's ultimate minimalist. They carry no electric charge and possess a mass so infinitesimally small that for decades, scientists believed they had no mass at all, traveling through the cosmos at the speed of light as pure, massless energy. While we now know they have a tiny, almost negligible mass, their velocity remains so extraordinarily close to the ultimate cosmic speed limit that, for all practical purposes, they are light-speed travelers. This incredible speed, combined with their refusal to interact with normal matter, makes them cosmic messengers of a unique and powerful kind, carrying information from the most violent events directly and without delay. They are so reluctant to interact that trillions of them pass through your body every single second, day and night, without a single one ever leaving a trace, flying straight through the solid Earth as if it were empty space. This profound aloofness was spectacularly demonstrated during one of the most significant astronomical events of the 20th century, supernova 1987A. On February 23, 1987, light from the explosion of a massive star in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, finally reached Earth, captivating astronomers around the globe. But hours before that first flash of visible light was seen, something else had already arrived. Deep underground, in massive, heavily shielded detectors designed to catch the rare neutrino interaction, instruments registered a sudden, unmistakable burst. Over a span of just 13 seconds, about 24 neutrinos were recorded. This might sound like a trivial number, but for experiments that might see a handful of random neutrinos on a normal day, this was a flood, a specific, statistically significant signal announcing a cosmic catastrophe. These neutrinos had been produced in the very first instance of the core collapse supernova during the frantic, seconds-long collapse of the stellar core into a neutron star. They had escaped the dying star at the speed of light, while the visible shock wave had to spend hours fighting its way out through the star's dense outer layers. The neutrinos were the heralds, the advanced scouts that arrived hours before the electromagnetic news, carrying the first and most direct evidence of the star's death. The implications of this detection were monumental, providing a brilliant and direct confirmation of two fundamental principles of physics. First, it proved that neutrinos do indeed travel at the speed of light, or so immeasurably close to it that the difference is negligible over cosmic distances. The light and the neutrinos had begun their 168,000-year journey from the Large Magellanic Cloud at the same instant, and they arrived at Earth within hours of each other. The slight delay for the light was not due to a slower travel speed, but to its slower escape from the turbulent aftermath of the explosion. Second, and perhaps more profoundly, the detection powerfully confirmed just how weakly neutrinos interact with matter. The supernova had unleashed a tsunami of neutrinos, an estimated 10 to the power of 58 of them. The fact that only 24 were recorded on Earth after that immense flock had traveled across 168,000 light-years of space is a testament to their almost supernatural ability to pass through anything and everything. This ghostly nature is what makes them so difficult to detect, requiring enormous, sensitive instruments buried deep underground to shield them from other cosmic radiation, waiting patiently for the 1 in a trillion chance that a neutrino will deign to interact with an atom in their vast volumes of water or heavy ice. Neutrinos are not just passive ghosts, they are active participants in the most energetic processes in the universe, acting as a primary cooling mechanism for stellar cores and supernova. In the final moments of a massive star's life, the collapsing core becomes so unimaginably dense and hot that protons and electrons are forced together, forming neutrons and releasing a torrent of neutrinos in a process called neutronization. This neutrino burst carries away a staggering amount of energy, roughly 10% of the star's total mass energy, according to Einstein's E = mc², in a matter of seconds. This rapid energy loss is crucial for the supernova mechanism itself, helping to blow the star apart. The study of these particles, born in such extreme environments and arriving at our detectors virtually untouched, has opened an entirely new window on the universe. Neutrino astronomy allows us to peer directly into the hearts of exploding stars and the dense, active cores of galaxies, processes that are often completely obscured from traditional telescopes by dust and gas. They are the perfect cosmic couriers, delivering their messages at the universe's ultimate speed, unaffected by the magnetic fields, radiation, and matter that can distort, block, or delay every other form of information we receive from the depths of space. This grand, inevitable merger with Andromeda is a story written in two distinct types of motion, and while its headlong rush toward us captures all the attention, there's a far more subtle and difficult-to-measure component that holds the key to the exact choreography of this future cosmic dance. We've already seen how Andromeda is blue-shifted, its light compressed as it barrels toward us at about 110 kilometers per second. That tells us the radial velocity, the speed directly along our line of sight. But like a ship on the ocean, it also has a transverse velocity, a slight, sideways drift across the vastness of the sky. This apparent motion against the backdrop of even more distant galaxies is what astronomers call its proper motion, and for an object 2.5 million light-years away, detecting this tiny shift is one of the most formidable challenges in all of observational astronomy. The scale of the difficulty is almost absurd. Imagine trying to measure the movement of a single hair on a person's head from a distance of 10 kilometers. Now scale that up to an interstellar level. The angular shift we're trying to detect for Andromeda is on the order of micro-arcseconds per year. A single micro-arcsecond is an angle so vanishingly small that it's the apparent size of a quarter on the surface of the Moon as seen from Earth. To measure a change that minute requires not just powerful telescopes, but immense patience and a level of precision that pushes our technology to its absolute limits. For decades, this measurement was simply beyond our reach. Astronomers had to rely on complex models and assumptions to guess at the galaxy's sideways motion, which meant the future collision with the Milky Way was a prediction with a wide range of possibilities, from a direct head-on impact to a gentler, glancing gravitational encounter. This all changed with the incredible power of the Hubble Space Telescope. In a feat of astronomical patience and precision, scientists used Hubble to meticulously observe specific regions within the Andromeda galaxy over a 5-year period. They didn't target the bright, blurry spiral arms, but instead focused on 2 distinct populations of stars that serve as perfect celestial landmarks. The first were faint, sun-like stars in the crowded hub of Andromeda's bulge. The second were exotic, volatile blue stars in its sprawling disk. By tracking the subtle, collective shift of these stars relative to the fixed positions of distant quasars, the most stationary background references in the entire universe, the Hubble team finally succeeded. They pinned down Andromeda's transverse velocity, revealing that it is moving sideways across our line of sight at a speed of approximately 17 kilometers per second. While that's minuscule compared to its 110 kilometer per second approach, this seemingly minor detail is the final piece of the orbital puzzle. So, what does this 17 kilometers per second of sideways drift mean for the fate of our galactic home? It transforms the prediction from a vague forecast into a precise, calculated destiny. When you combine this transverse motion with the known radial velocity, you can plot the true, 3-dimensional path of Andromeda through space. This refined trajectory confirms that a direct, head-on collision between the 2 galactic cores is highly unlikely. Instead, the merger will begin with that dramatic but non-fatal first close pass we discussed. The newfound precision of the sideways motion allows astronomers to run supercomputer simulations with far greater accuracy, showing that in about 4 billion years, the Milky Way and Andromeda will sweep past each other, their gravitational embraces pulling out immense, luminous tidal tails of stars and gas. They will then swing back together, their orbits gradually decaying over another 1 to 2 billion years through a process known as dynamical friction, before finally settling into a single, new, ellipsoidal galaxy. That small, sideways kick is the gentle nudge that ensures the initial encounter will be a spectacular, structure-wrecking gravitational tango rather than a single, catastrophic head-on crash. It's the difference between a slow, majestic dance of mutual consumption and a single, violent, and final merger. This incredible measurement reminds us that in cosmology, the smallest, most difficult-to-detect motions can hold the ultimate key to understanding the grandest of future events. But to truly appreciate the staggering velocities at play around a black hole, we must look beyond the frantic orbits of the accretion disk and examine the very fabric of spacetime itself. This brings us to a region where Einstein's theory of general relativity makes one of its most dramatic predictions, a place where the distinction between a spinning object and the space it occupies completely dissolves. Imagine a black hole that isn't just a static, gravitational pit, but a cosmic whirlpool spinning at a significant fraction of light speed. This is a Kerr black hole, named after the mathematician who solved Einstein's equations for a rotating mass, and its environment is far stranger than its non-spinning or Schwarzschild counterpart. While both have an event horizon, the point of no return, the Kerr black hole is surrounded by a mind-bending region called the ergosphere. Think of this as a flattened, pumpkin-shaped zone of twisted spacetime that lies just outside the event horizon. Within this ergosphere, something truly incredible happens. Space itself is not merely curved, it is dragged forcefully and relentlessly around the black hole in the direction of its spin. This phenomenon is known as frame dragging. The concept of frame dragging is akin to placing a heavy, rapidly spinning ball in a thick, viscous fluid like honey. As the ball rotates, it would pull the surrounding honey into a swirling motion. In the case of a Kerr black hole, spacetime itself behaves like that fluid. The immense mass and rapid rotation of the black hole create such a profound gravitational vortex that the very coordinate grid of the universe is wrenched into a circular motion. This isn't a gentle tug. The rotational velocity of this dragged space can reach speeds approaching that of light at the outer boundary of the ergosphere. This creates a cosmic dictatorship of motion. Any object, even light itself, that enters the ergosphere is forced to co-rotate with the black hole. It is physically impossible to stand still relative to the distant stars. You are caught in a current of moving space and must move with it. You still have a chance to escape if you haven't crossed the event horizon, but your path is no longer your own. You are a twig caught in a relativistic river, compelled to flow in the direction of the current. This leads to one of the most fascinating and counterintuitive consequences imaginable: the possibility of extracting energy directly from a black hole's rotation. This theoretical process, known as the Penrose process, turns the black hole from a purely consumptive monster into a potential power plant. Imagine an advanced civilization sending a probe into the ergosphere. The probe is programmed to split into two pieces. One piece is directed to fall into the black hole, following the irresistible flow of space-time, while the other is designed to escape. Here's the trick: if the timing and trajectory are perfect, the piece that falls in can be given a negative energy orbit relative to an observer at infinity. In this bizarre relativistic accounting, the black hole actually loses a tiny amount of its rotational energy. To conserve total energy, the other fragment of the probe is flung back out of the ergosphere with more energy than the original probe had when it entered. Essentially, the probe has stolen rotational energy from the black hole itself. While this is a highly idealized thought experiment, it demonstrates a profound principle. A rotating black hole is not a dead end. It is a dynamic object storing an immense amount of energy in its spin, an energy that, in theory, could be mined by any civilization with a sufficiently advanced understanding of physics. The effects of this frame dragging are not just theoretical fantasies confined to the edges of black holes. We have actually measured this phenomenon here in our own solar system, albeit on an infinitesimally smaller scale. Our rotating Earth also drags space-time around with it, though the effect is incredibly weak. To detect it, NASA launched the Gravity Probe B mission, a satellite containing the most perfect spherical gyroscopes ever manufactured. In a universe without frame dragging, the spin axes of these gyroscopes would always point in the same fixed direction relative to a distant guide star. But over time, scientists observed a tiny, precise drift in the orientation of the gyroscopes. This minuscule precession was the direct result of the Earth's mass twisting the local spacetime around it, pulling the gyroscope's frames along for the ride. The measured effect perfectly matched the predictions of general relativity. This extraordinary experiment confirmed that the fabric of reality is not a static stage. It is a dynamic entity that is molded and stirred by every rotating mass within it. What is an almost imperceptible whisper around our planet becomes a screaming hurricane around a Kerr black hole, a place where space moves at the ultimate speed limit and the universe reveals one of its most profound and active secrets. While massive objects like black holes and neutron stars can generate gravitational waves powerful enough for us to detect directly, the influence of these space-time ripples is not limited to such violent cosmic-scale events. In fact, the gentle, persistent emission of gravitational waves is a universal phenomenon, a quiet hum that accompanies any system with mass in motion, gradually reshaping the cosmos one orbit at a time. This leads us to a system that, while far less dramatic than a black hole merger, provided the first brilliant and undeniable proof of this energy loss. The story begins in 1974 when astronomers Russell Hulse and Joseph Taylor discovered a truly unique celestial object, a binary pulsar now known as pulsar B 1913+16, or the Hulse-Taylor pulsar. This wasn't just one neutron star, but two, locked in an incredibly tight, fast, and eccentric dance around each other. One of them was a pulsar, its lighthouse-like beam of radio waves providing a perfect, high-precision clock for astronomers to track its motion with exquisite accuracy. According to Einstein's theory of general relativity, any system with accelerating masses will produce gravitational waves. Imagine two enormous stars whirling around each other at a significant fraction of light speed. Their immense motion creates a continual distortion in the fabric of space-time, sending out ripples that propagate outward at the speed of light, much like a boat circling in a pond sends out expanding waves. But these waves don't travel for free, they carry energy away from the system itself. This slow, steady drain of energy has a direct and measurable consequence. It causes the two stars to lose orbital energy. As their orbital energy decreases, they must move closer together to compensate, causing their orbits to very, very slowly decay. The stars begin a long, patient spiral inward, a process astronomers call inspiral. In the case of the Hulse-Taylor binary, the predicted effect was incredibly subtle. The orbital decay due to gravitational waves amounts to a change of just a few meters per second in the orbital velocity, and a shrinkage of the orbit by about 3.5 meters per year. That's a change so minuscule it would be like measuring the slow, imperceptible thinning of a human hair from a distance of 10 kilometers. This is where the Hulse-Taylor pulsar became a gift to science. The clock-like precision of the pulsar's radio pulses allowed astronomers to map the orbit of the two neutron stars with a level of detail that was previously unimaginable. Over years and then decades, they meticulously timed the arrival of each pulse. Because the pulsar moves in its orbit, sometimes toward us and sometimes away, the pulses are minutely affected by the Doppler effect, arriving slightly early or late in a precise repeating pattern. By tracking this pattern with extreme care, they could measure the exact shape and period of the orbit, and as the years turned into decades, a clear and undeniable trend emerged. The orbital period of the system was getting shorter. The two neutron stars were, ever so slightly, completing their frantic dance around each other a little bit faster each year. They were spiraling inward exactly as predicted by general relativity, and at precisely the rate that would be expected if they were losing energy by radiating gravitational waves. The data wasn't just close, it was a perfect match, a stunning confirmation of a key prediction of Einstein's theory that earned Hulse and Taylor the Nobel Prize in Physics in 1993. The significance of this discovery cannot be overstated. It was the first indirect but overwhelmingly convincing proof that gravitational waves are real. This was not a laboratory experiment or a theoretical calculation. This was a direct observation of the dynamic, evolving universe behaving exactly as Einstein's equations said it should. The Hulse-Taylor binary pulsar became a natural laboratory for fundamental physics, allowing us to test the predictions of general relativity in a regime of incredibly strong gravity. The slow, meticulous decay of its orbit demonstrated that space-time is not a static stage, but a dynamic, flexible fabric that can be stirred into motion, and that this motion itself carries real energy away from massive systems. While it would take another 4 decades for the LIGO observatories to directly detect the chirp of a gravitational wave from a black hole merger, it was the patient, decades-long observation of this slowly inspiraling binary pulsar that first showed us the universe was quietly humming with the vibrations of moving mass, a subtle but relentless force that is, even now, gently reshaping orbits of compact objects throughout the cosmos. But among the brilliant stellar factories and the quiet red dwarfs, there exists a class of stars living life on the very edge, burning with such ferocious intensity that they are quite literally tearing themselves apart. These are the Wolf-Rayet stars, the final, volatile chapter in the lives of the most massive suns, and they are defined by one of the most powerful and sustained outflows of matter ever observed. If our sun's solar wind is a gentle breeze, then the wind from a Wolf-Rayet star is a continuous supersonic hurricane, a stellar gale of almost unimaginable force. These aren't mere gusts, they are a constant high-velocity exhalation where the star itself is evaporating into space at breathtaking speeds. The material being ejected isn't just a thin stream of particles, it's a thick, dense wind of heavily processed gas, and it races away from the stellar surface at velocities between 2,000 and 3,000 kilometers every second. To put that into a truly staggering perspective, at that speed, you could travel from the Earth to the Moon in just over 2 minutes. This is not a gentle shedding of mass, it is a stellar self-immolation, a desperate and powerful shedding of the star's own outer identity. What could possibly drive such an extreme and sustained loss of material? The answer lies deep within the star's core and its phenomenal luminosity. A Wolf-Rayet star is the exposed, bare core of a star that was originally 20 times more massive than our Sun or even larger. After burning through the hydrogen in its core, it advanced to fusing heavier elements like helium, carbon, and oxygen. In these final, frantic stages of its life, the nuclear reactions in its core generate an almost unbearable amount of energy. This energy output is so prodigious that the radiation pressure pushing outward from the star's interior becomes overwhelming. The very light streaming from the core exerts a force stronger than the star's own gravity on its outer layers. It's as if the star's internal furnace has been stoked to such a fever pitch that the resulting pressure simply blows the star's atmosphere away, layer by layer, in a relentless supersonic torrent. This process strips the star down, peeling back its outer hydrogen envelope to reveal the hot, helium-burning core beneath, which is furiously forging heavier elements like carbon, nitrogen, and oxygen. The stellar wind is so dense and so fast that it effectively removes the star's own outer shroud, leaving behind a brilliant blue-hot core that is rapidly marching toward its own destruction. This dramatic weight loss program has a profound effect on the star's ultimate fate and its legacy. A typical Wolf-Rayet star can lose a mass equivalent to our entire Sun in just 100,000 years. Think about the sheer scale of that, an entire solar mass, a quantity of material that could form 1,000 planets like Jupiter, being ejected into the void in a cosmic blink of an eye. This radical slimming means that by the time the star's core finally runs out of fuel and collapses, it has already shed a huge portion of its outer mass. This pre-supernova diet drastically alters the properties of the eventual explosion. Without this massive, dense envelope, the supernova shockwave has a much easier time bursting out, potentially leading to a different type of stellar explosion, such as a Type Ib or Type Ic supernova, which are notably lacking in hydrogen. The material that is lost doesn't just vanish, however. These high-speed winds act as a primary delivery system for the galaxy's chemical enrichment. As the wind blasts outward, it carries with it the freshly forged heavy elements from the star's interior, elements like carbon, oxygen, and nitrogen. This material is violently injected into the surrounding interstellar medium at tremendous speeds, where it slams into existing gas clouds, compressing them and seeding them with the building blocks for new stars, planets, and ultimately life. The famous intricate ring nebula surrounding the star Gamma Velorum is a stunning example of this. The beautiful shell-like structure is not a supernova remnant, but the accumulated debris from the star's own powerful wind, a glowing testament to the mass it has already shed. In this way, the ferocious, high-speed wind of a Wolf-Rayet star is not just a symptom of its impending death, but a vital, creative force, a galactic fertilizer that ensures the star's dramatic life will contribute to the birth of future cosmic generations. Yet even the self-destructive fury of a Wolf-Rayet star pales in comparison to the ultimate cosmic detonation, a release of energy so concentrated and violent that it can momentarily outshine every star in every galaxy in the observable universe combined. We now arrive at the breathtaking frontier of gamma-ray bursts, the universe's most powerful and elusive explosions. These are not the relatively slow, expanding fireballs of supernova. They are cosmic lightning strikes, incredibly brief and unimaginably bright flashes of the highest energy radiation. Lasting from a few milliseconds to a few minutes, a single gamma-ray burst can release more energy in that fleeting instant than our Sun will emit over its entire 10 billion-year lifespan. For a few seconds, this single, distant point in space becomes the brightest source of gamma rays in the entire cosmos, a beacon of pure violence that can be detected from billions of light-years away. The key to this phenomenal, focused power isn't just the raw energy involved, but the incredible, almost perfect efficiency with which it is delivered. That delivery mechanism is a jet, but not the kind we've encountered before. This is an ultra-relativistic jet, a beam of plasma and radiation so finely tuned and focused that it represents the pinnacle of speed and collimation in the universe. To truly grasp the nature of this jet, we must move beyond simple percentages and into the realm of a concept known as the Lorentz factor, a term from Einstein's special relativity that describes just how deeply an object is living in the universe's fast lane. While we've discussed particles and stars moving at 99.9% of the speed of light, the jets in gamma-ray bursts operate in a different league entirely, with Lorentz factors that can exceed 1,000. What does this number actually mean? Essentially, it's a measure of the extreme effects of time dilation and length contraction. For an object with a Lorentz factor of 1,000, time for that object slows down by a factor of 1,000 relative to a stationary observer. Its length in the direction of motion contracts by the same factor, and its mass effectively increases 1,000-fold. To achieve such an extreme Lorentz factor, the material in the jet must be moving at 99.9999% of the speed of light. At this velocity, you are only traveling about 3 centimeters per second slower than light itself. This isn't just fast, it is matter teetering on the absolute brink of the possible, its properties warped beyond our everyday intuition. This mind-numbing velocity is not an incidental feature. It is the very engine that creates the unique observational signature of a gamma-ray burst. The initial, intense flash of gamma rays that gives these events their name is a direct result of this ultra-relativistic motion. The jet is not a smooth, uniform beam. It is internally turbulent with different shells of material moving at slightly different speeds. When a faster-moving shell catches up to a slower one, they collide in a process known as internal shock dissipation. Because the jet is moving so close to light speed, these collisions are phenomenally violent. The kinetic energy of the motion is instantly converted into a firestorm of gamma-ray photons. Furthermore, due to the extreme relativistic effects, the radiation we observe is dramatically amplified and compressed. The light that would normally be emitted in other wavelengths is, from our perspective, massively blue shifted into the high-energy gamma-ray part of the spectrum. The duration of the event is also compressed. What might be a longer-lasting eruption in the jet's own frame of reference is squeezed into a blindingly short flash from our point of view. Without this incredible speed, a gamma-ray burst would simply not look like a gamma-ray burst. It would be a slower, dimmer, and much broader event, lost in the background glow of the cosmos. The story does not end with the initial flash. As this bullet of plasma continues to travel outward, it eventually begins to plow into the tenuous interstellar medium that exists even in the depths of intergalactic space. This is where the second act of the drama unfolds, the afterglow. The collision with the external medium creates a powerful shock wave known as the external shock. This shock wave acts as a colossal particle accelerator, even more powerful than the supernova shocks we discussed earlier. It energizes electrons to fantastic speeds, causing them to spiral around magnetic field lines and emit radiation across the electromagnetic spectrum, from X-rays and visible light down to radio waves. This afterglow can persist for days, weeks, or even months, slowly fading away. For astronomers, this afterglow is a gift. The initial gamma-ray flash tells them when and roughly where to look, but it's over too quickly to study in detail. The afterglow, however, allows them to point optical and radio telescopes at the location, measure its redshift to determine the burst's colossal distance, and study the environment of the explosion. It was through afterglow observations in the late 1990s that astronomers definitively proved gamma-ray bursts were not local phenomena within our galaxy, but cosmological events occurring in distant galaxies, making their prodigious energy output all the more staggering. The existence of such a perfect, natural particle accelerator begs the question, what cosmic forge could possibly create it? The leading theories point to the most extreme stellar deaths imaginable. For the short-duration gamma-ray bursts, the culprit is thought to be the merger of two ultra-dense objects, like neutron stars or a neutron star and a black hole. As these objects spiral together and finally merge, they can unleash a tremendous amount of energy and, for reasons still being unraveled, channel a portion of it into those ultra-relativistic jets. For the long-duration bursts, the engine is believed to be the death of a truly monstrous star, perhaps tens of times the mass of our Sun, in a supernova event so extreme it's dubbed a hypernova. In this scenario, the collapsing core doesn't form a standard neutron star, but immediately collapses into a black hole, as vast amounts of stellar material rain down onto this newborn black hole. Its immense rotation and magnetic fields are thought to power up the jets, which then have to drill their way out through the body of the star itself. The jet's incredible focus and speed are a testament to the clean, efficient violence of its birth, a final, focused scream from a star undergoing the most dramatic transformation the universe can provide. After a journey across the cosmos, from the frantic spin of subatomic particles to the majestic drift of entire galaxies, we arrive at the ultimate, most profound extreme of speed, a form of change so slow it represents the final, fading breath of the universe itself. This is not a velocity in the traditional sense, but a rate of transformation, the gradual slide toward a state of cosmic equilibrium known as the heat death. Governed by the unyielding second law of thermodynamics, this process dictates that the total entropy or disorder of a closed system can only increase over time. Imagine the universe as a cup of hot coffee left in a room. At first, there's a sharp temperature difference, a strong energy gradient between the hot coffee and the cooler air. This gradient allows for work to be done. It drives the transfer of heat, creating steam, causing convection currents, and eventually warming the room. But over time, the coffee cools, and the entire system reaches a single, uniform, lukewarm temperature. No more energy can flow, no more work can be accomplished. The system has reached a state of maximum entropy, a static and silent equilibrium. Our universe is on that exact same path, just on an almost inconceivably grander scale. Currently, our cosmos is vibrant and dynamic precisely because it is filled with steep energy gradients. We have the searing inferno of stars blazing against the near-absolute zero cold of deep space. We have the immense gravitational potential of black holes and the frantic kinetic energy of swirling galaxies. These disparities are what power every single process we've explored, from nuclear fusion in stellar cores to the very chemical reactions that make life possible. But the second law is a one-way street. Energy constantly disperses, spreads out, and evens out. Stars burn through their fuel and die, their light and heat radiating into the void. Black holes slowly evaporate over eons through Hawking radiation. Even the protons that make up the very fabric of matter may eventually decay, transforming their mass into a faint, final whisper of energy. Each of these events is a step toward erasing the cosmic gradients, smoothing out the universe's wrinkles until there are no hot spots or cold spots left, no high-pressure zones or low-pressure zones. just a vast, featureless, and incredibly thin sea of particles and radiation, all at the same infinitesimally low temperature, just a fraction of a degree above absolute zero. The timescales involved in this final act are where the concept of slowness achieves its most extreme form. We are not talking about billions or even trillions of years. The stellar era, where new stars are born, will likely end in about 100 trillion years. The subsequent degeneration era, where white dwarfs cool and black holes dominate, will last for trillions upon trillions of years more. But the true heat death unfolds over timescales that make these periods seem as brief as a single heartbeat. The slowest known theoretical process, the potential decay of a proton, has a hypothetical half-life in the range of 10 to the power of 34 years or more. To even begin to comprehend a number like that, consider that the entire current age of our universe is only about 10 to the power of 10 years. A single 10 to the 34-year span is a 1 followed by 34 zeros, a duration so long that if you counted every second since the Big Bang, you wouldn't even have made a dent. During this unimaginable expanse of time, the last remnants of structure will have long since vanished. Galaxies will have evaporated, stars will have burned out and cooled to black, and black holes themselves, once thought to be eternal, will have radiated away their mass, popping out of existence in a final, quiet puff of energy. The universe in this final state would be a place of profound stillness and darkness. With no energy gradients, no work can be performed. There can be no motion, no change, no complex structures, and certainly no life. It is the ultimate end of all processes, a state of maximum entropy where the cosmic arrow of time itself effectively ceases to have any meaning, as there are no longer any discernible events to mark its passage. This isn't a violent end, not a big crunch or a dramatic rip. It is a quiet, gentle, and infinitely patient fade to black, a final equilibrium where the universe, having exhausted all its potential for action, settles into a permanent and uniform slumber. This crawling pace toward absolute stillness is the ultimate, and perhaps most humbling, extreme of speed, a reminder that all the frantic motion and brilliant energy we see today is but a temporary, fleeting phase in an unimaginably long and increasingly quiet cosmic story. After exploring the profound slowness of cosmic heat death, it's almost startling to return to a simple, tangible fact about light that we can observe right here on Earth, a phenomenon that seems to contradict everything we've established about the universe's ultimate speed limit. We've spent this journey marveling at light's unwavering constancy in the vacuum of space, but here's a twist that brings this cosmic rule right into our daily lives. Light itself can be slowed down. Not in the empty void, but here, in our own world, when it passes through a material like water, glass, or even air. This is not a violation of relativity. It is a beautiful demonstration of how light interacts with matter, and it's the reason we have rainbows, lenses in our glasses and cameras, and the mesmerizing shimmer of a swimming pool. The key to understanding this lies in a fundamental property of any transparent material known as its index of refraction. Think of empty space as a perfect, frictionless superhighway where light can travel at its maximum possible speed, 299,792,458 meters per second. Now imagine light entering a medium like glass. This is not an empty highway anymore. It's a crowded street filled with atoms and electrons. As a light wave enters this crowd, its oscillating electric field causes the charged particles within the atoms to vibrate. These vibrating particles don't just sit there. They themselves become tiny transmitters, re-radiating the light wave, but with a tiny, almost imperceptible delay. The overall light wave that emerges from the material is actually a complex combination of the original wave and all these countless re-radiated waves from the atoms in its path. The net effect of this intricate dance is that the wave as a whole is forced to slow down, even though the individual interactions between photons and atoms still occur at the speed of light. The index of refraction is simply a number that quantifies this slowing effect. For air, it's almost 1, meaning light is barely slowed. For water, it's about 1.33, meaning light travels at only 75% of its vacuum speed. For diamond, it's a high 2.42, slowing light to a relative crawl. This is why a diamond sparkles so brilliantly. The high refractive index causes light to bend sharply and reflect internally, trapping it in a dazzling play of colors before it finally escapes to your eye. This reduction in speed has a direct and visible consequence. It causes light to change direction, a phenomenon we call refraction. Imagine a marching band moving in a straight line on a dry field, with all members perfectly in step. Now suppose the band hits a patch of mud. The marchers on one side of the formation hit the mud first. Since it's harder to move through the mud, their pace instantly slows. The marchers still on the dry ground, however, continue at their original, faster speed for a few more steps. This difference in speed between the two sides of the formation causes the entire band to pivot, changing its direction of travel as it enters the muddy area. Light behaves in exactly the same way. When a beam of light enters a new medium like water at an angle, one part of the wavefront hits the water and slows down first, while the rest of the wavefront is still moving at the faster air speed. This speed differential causes the entire beam to bend toward an imaginary line perpendicular to the surface, known as the normal. When it exits the water back into the air, the reverse happens. The part of the wave that leaves first speeds up, causing the beam to bend away from the normal. This is why a straw in a glass of water looks broken at the surface. The light from the submerged part is bending as it exits the water, making the straw appear to be in a different location than it actually is. This principle of refraction is harnessed by one of humanity's most transformative inventions, the lens. A lens is simply a carefully shaped piece of glass or other transparent material designed to bend light in a specific, controlled way. A convex lens, which is thicker in the middle, causes parallel rays of light to converge to a single point known as the focus. This is the fundamental operating principle of a magnifying glass, a camera lens, and even the lens in your own eye, which focuses incoming light onto your retina. A concave lens, which is thinner in the middle, does the opposite, causing parallel light rays to spread out or diverge. By combining different lenses, we can correct faulty vision, build powerful telescopes to see distant galaxies, and create microscopes to reveal the hidden world of cells and bacteria. The entire science of optics, which underpins so much of our modern technology from fiber optic internet to laser surgery, is built upon this single, profound fact that light changes speed when it moves through matter. Perhaps the most beautiful and universal demonstration of this variable speed is the rainbow. Sunlight, which appears white to our eyes, is actually a mixture of every color of the rainbow, each color corresponding to a different wavelength of light. When a beam of sunlight enters a spherical raindrop, it slows down and refracts, bending as it enters the water. But here's the crucial part: different wavelengths of light are slowed by slightly different amounts. Shorter wavelengths like violet and blue light are slowed more effectively and therefore bend more sharply. Longer wavelengths like red and orange light are slowed slightly less and bend a little less. This separation of white light into its constituent colors is called dispersion. After refracting upon entry, the light travels across the raindrop, reflects off the inner back surface, and then refracts again as it exits the drop back into the air. This second refraction further amplifies the separation of colors. Because of the geometry of the raindrop and the specific angles involved, each color is sent back toward your eye from a different set of raindrops. You see red light coming from raindrops higher in the sky and violet light from raindrops lower down, with all the other colors arrayed in between, creating the magnificent, colorful arc that has inspired wonder for all of human history. So, the next time you see a rainbow arching across a stormy sky, remember that you are witnessing a spectacular cosmic speed trap, where sunlight is being subtly slowed and sorted by countless tiny water droplets, transforming the uniform white of the sun into a brilliant spectrum of color. It's a perfect reminder that even the most extreme and fundamental rules of the cosmos can manifest in the most familiar and beautiful ways, connecting the physics of the distant universe to the simple wonders of our own world. And so, our breathtaking tour across the spectrum of cosmic velocity draws to a close. We have journeyed from one extreme to the other, from the patient, fingernails-pace crawl of continents that builds mountains over eons to the frantic millisecond flicker of a black hole's accretion disk. We have witnessed the solitary wanderings of hypervelocity stars flung from the galactic core, the stately 230 million-year orbit of our solar system, and the relentless universe-wide recession of galaxies in the Hubble flow. We have seen how the slow decay of radioactive atoms warms our planet's heart, and how the sudden, catastrophic collapse of a stellar core can blast a shockwave across space at 30,000 kilometers per second. From the gentle drift of a glacier to the screaming hurricane of a Wolf-Rayet star's wind, and from the silent, ghostly passage of a neutrino to the focused, ultra-relativistic fury of a gamma-ray burst jet, we have seen that speed is the fundamental language of cosmic change. It is the variable that dictates the rhythm of existence, governing everything from the formation of a single planet from specks of dust to the ultimate heat-death fate of the entire cosmos. These are not abstract numbers in a textbook. They are the very forces that sculpt our reality, the dynamic expressions of energy and time that write the story of every star, every galaxy, and every atom. This incredible range, from the imperceptibly slow to the unimaginably fast, reveals a universe that is profoundly dynamic at every scale. The same physical principles that guide the gentle spiral of a protoplanetary disk also govern the chaotic whirl of a galaxy cluster. The patient persistence of a creeping glacier carves landscapes with the same transformative power as the violent, fleeting impact of a meteor. The universe operates on clocks calibrated for both the lifetime of a proton and the spin of a pulsar, proving that there is no single, correct pace for significance. A force, no matter how weak, becomes world-shifting when applied over a sufficiently long time, just as a burst of unimaginable energy, lasting only milliseconds, can seed future generations of stars with the elements for life. Understanding these extremes is not just about setting records, it is about comprehending the interconnected nature of the cosmos, seeing how the slow, geological processes of our planet are linked to the explosive deaths of distant suns, and how the steady spin of our galaxy is itself part of a grand gravitational dance that will one day see it merge with its neighbor. In the face of this cosmic choreography, our own place is one of profound humility and equally profound wonder. We are transient beings living on a timescale of heartbeats, yet we have developed the intellect to measure the spin of a city-sized star from thousands of light years away and to predict the slow, inevitable merger of galaxies billions of years in the future. We are carried on a planet spinning at supersonic speeds, orbiting a star sailing through the local interstellar cloud, all within a galaxy racing toward a destiny of collision and rebirth. Our entire history, every triumph and tragedy, has unfolded within a single, quiet galactic year. And yet, from this tiny vantage point, we have managed to map the expanding fabric of spacetime itself and to listen for the faint ripples from colliding black holes. We are both insignificant in the grand, cosmic sweep of time and space, and spectacularly unique in our ability to observe, question, and marvel at it all. The universe is a symphony of motion, and we have only just begun to learn its notes. If this journey through the extremes of cosmic speed has sparked your curiosity, then the adventure is far from over. We would love to hear which fact amazed you the most. Was it the single, oh my God, particle carrying the energy of a pitched baseball, the star flung from the galaxy like a cosmic cannonball? or the gentle centimeter-per-year retreat of our own moon? Share your favorite mind-bending speed in the comments below. Let's continue the conversation. If you enjoyed this voyage across the cosmos, be sure to like this video and subscribe to the channel for more deep dives into the wonders of the universe. Until next time, keep looking up and never stop marveling at the incredible, dynamic, and beautifully violent cosmos we are